बरोबर आहे पण लागलं नाही येस कॅन यू से समथिंग
Hello? Yeah, I think.
ओके रेकॉर्ड होत आहे ना ओके थँक्यू
So just to add one or two sentences to whatever Kunj is saying, that please not be under the impression that what is happening here is something irrelevant. You know, you will be using all these concepts and techniques which I'm telling you, or all the teachers are telling you, actually while practicing quantum computing. I assure you that there is absolutely no problem. Okay, so let me start now. So yesterday we defined what are called these orthogonal states, and so we saw that two states are orthogonal if their scalar product vanishes. And this is not a new concept in actual practice in our three-dimensional thing. If two vectors are orthogonal, their scalar product A dot B vanishes. A and B are orthogonal. So it's the same thing. It is here the scalar product is vanishing. Now there is one thing that I can show you that if there are two states which are orthogonal, then they are also linearly independent. So let me suppose you have C1 psi plus C2 phi equal to 0. Okay, so it's a linear combination, and I am equating it to 0. So that means or whatever you can have, say alpha or whatever, it doesn't matter. So I can take 0, I justify it, so there is no problem. So what I'll do is I'll take first the scalar product with respect to phi. So I'll get C1 phi psi plus C2 phi phi equal to 0. Now phi, if it is normalized, as I told you yesterday, the scalar product of a normalized state with itself is 1. So this is 1 and this is 0. So C2 into C2 is equal to 0. Similarly, if I take the scalar product with respect to psi, then I get C1 psi plus C2 psi phi. Here it is 0 and this is 1. So C1 is equal to 0. C2 equal to 0 here and C1 equal to 0 here. That means if psi and phi are orthogonal, you can, any linear combination equating it to 0 will give me both the coefficients 0. That means they are linearly independent.
Does not exist any C1, C2, non-zero C1, C2.
Non-zero C1, C2 by which you can make a linear combination. So orthogonality means this. Now let us let us see something more.
It is orthogonality implies linear independence.
Linear independence. Orthogonality implies linear independence. That is right. So now I had already started it yesterday, so let me complete that. So I have a state psi, and I have an orthonormal basis. Yeah, if you are researching something about this, what I am teaching, please be allowed. Please just tell me what is your problem.
No, C1, C2 are only complex numbers.
Yeah. But they are 0. I mean, that there is no question. In general, they will be complex because quantum states forms a linear space with whose scalars are complex numbers. Scalars means the coefficients that occur in the linear combination of the elements of that space. Is that clear? Okay, those are complex numbers. So psi. Okay, so psi I write as a superposition, say Ck K. The orthogonal basis, which I will just K runs from 0, 1, 2, 3. So this is, these are the states, and the total number of states in that basis is what? Dimension. The total number of states in the basis is the dimension. So dimension, say, equal to n. So I get, say, k equal to 0 to, say, n minus 1, whatever that is. Now what I will do is I will fix some particular state out of this basis, Lth state. I just choose one state out of the basis and I take a scalar product. So I will get L on both sides. So I will get this scalar product here, that is equal to summation of k running from 0 to n minus 1 Ck Lk. L is a fixed number, it's a fixed one chosen basis state. Okay. So what can you say about this?
CL.
This is,
CL.
this will be non-zero
K equal to L.
when only when k is equal to L and 0 otherwise, because it's a orthonormal basis. That is, any pair of states in this basis are orthogonal and each of them is normalized. Do you get it or no? नहीं नहीं का नहीं समझला काल आपण बघितलं ना. सी एक मिनिट. psi is supposed to be just take it. psi is supposed to be normalized if this is the case.
सर वो 2D वेक्टर से बता दीजिए.
हाँ हाँ
They will
हाँ.
understand better. You have a vector, right?
No, no.
X, Y, Z. So they are orthogonal.
And normalized in your case is just its length is 1.
Yes. So similarly, norm is the
Norm is the length of that
abstract form of
state.
length.
Abstract form of length. So length is 1. So that means its scalar product with itself is 1. Okay. So if A is a vector whose length is 1, then A dot A is equal to 1. So like this. I mean, you will prove this in your what is that? Discussion. Okay. Active learning. Okay. So that is right. So fine. So this is the case. So when L is equal to K, this is 1. And if L is not equal to K, this is 0. So out of all this sum, only Lth term will survive. K equal to L will survive. And its value is 1. So you will have this is equal to.
Sir, we do it in Fourier series in order to find out the coefficient of the.
No, this is not a Fourier series.
No, we do this type of maths.
Yeah. This is very fundamental. You will use it at many places. No problem. Okay. So this technique, taking scalar product with of orthogonal states, you will be using it at many places. So only.
From engineering point of view, orthonormality always helps at the receiver side to get the coefficient of the corresponding.
That is because they are distinguishable. We'll come. We'll come to that. We'll come to that. Okay. So no. This is also important for quantum computation. So that means Lth coefficient in this superposition is given by the scalar product of Lth state with psi. So that means the probability of I mean, if I have a state psi and if I make a measurement to this basis, I mean, this is suppose, I mean, okay, so I have to tell you something more. Okay, so I have taken a general basis here, some general basis with orthonormality. But now, if I take an observable, say A, and collect all its eigenstates, say K again, K running from 0, 1, 2, 3. These are the collection of all eigenstates of A. Okay. And if I make a measurement of A on this on some state psi, there is some state psi, I make a measurement of A on this side, then I will get some eigenvalue and some eigengate, say Lth eigenstate or some, whatever that is. Okay, and what is the probability of, I mean, with the corresponding probability, I mean, I want to find out that probability. For that, what I have to show you that this forms an orthonormal basis. The set of eigenstates of a observable, generally, I mean, the eigenstates belonging to different eigenvalues are orthogonal. eigenstates belonging to the same eigenvalue. You can have two linearly independent eigenstates belonging to the same eigenvalue, but that I can orthogonalize. I will not go into that, but you can orthogonalize and you can make it a orthonormal basis. Okay, so so how do I prove it? How do I say it? What is the physical argument? The argument follows from the basic assumption that if put in an eigenstate into the measurement apparatus, then I get the same eigenstate out. Okay. So if I put an eigenstate, I cannot get any other eigenstate belonging to some different eigenvalue. Okay, I cannot get an eigenstate out which belongs to some different eigenvalue. I am going slow, you can understand this. But then for that, suppose I get some eigenstate, say nth eigenstate, I put into this okay, and suppose I want this nth eigenstate out exactly without any approximation, then it means that the probability of getting some other eigenstate must be 0. But what is that probability? That probability is, suppose some other eigenstate, say mth eigenstate. So what is the probability of getting mth eigenstate out? Is this. This is the probability, you see, here. And I want this to be 0 because by my basic assumption, if I put an eigenstate, I must get that eigenstate out with probability 1, no approximation. The probability of getting any eigenstate belonging to some other eigenvalue has to be 0. But that probability is this. So this has to be 0. That means has to be 0. This scalar product between the basis, the states must be 0. That means they are all mutually orthogonal. But now we have just proved what? That they are also linearly independent. That means they form a orthonormal basis. The set of eigenstates forms a basis in the first place, and it can be converted into orthonormal basis. What we have proved is that if you have eigenstates belonging to two different eigenvalues, they have to be orthogonal. We have proved already. But suppose you have eigenstates belonging to the same eigenvalue, then they have to be, they can be orthogonalized. And I am not going to go into that detail. But take it from me, believe in me that they can be orthogonalized. And therefore you can make this basis comprising all eigenstates of an observable to be an orthonormal basis. Okay? Any problem until now? Okay. So this is this is now. So where I was? Yeah, okay. So okay, let me get out of this. Now let us about distinguishability. That I have to discuss this. So distinguishability of two states, whether I can distinguish reliably between these two states. Suppose you are given some quantum particle, a qubit or whatever you want to call it, and I tell you that this particle is either in state psi or in state phi. This information is given to you. How will you decide which of these two states the particle is in? This is the problem of distinguishability. Okay? So the definition of the distinguishability is this, that suppose there is an observable A and I have some arbitrary state. This is my method of putting some arbitrary state, and there is some particular eigenstate. Okay. Now you are given the information that the particle is in either this state or that state. This is one of the eigenstates, this is some arbitrary state.
आर्बिट्रीला डॉट म्हणतात.
म्हणतात नाही, माझं नोटेशन आहे ते, म्हणत नाही. डॉट मीन्स यू रीडिंग एनिथिंग इन देयर, इट डजंट मॅटर हियर, बट डजंट मॅटर. ओके, so this is what this problem is. Now what I do is, what is possible for me is to make this measurement. Okay, so suppose I make measurements on this. I mean, I make a measurement on this and measurement on this, and the results of these measurements I want to use to find out whether they are distinct or not. I mean, now suppose I put that particle inside. Okay, it has to be either in the dot state or the lambda state. Okay, if I put it inside, and if it comes out of this is 0, then what can you say? Can you distinguish between the states? I mean, suppose this is 0. I'm sorry, I call it 0. I mean, you are told that this is either in dot state or 0 state, get 0 state. I put it into the measurement apparatus and it comes out of this channel, one channel. What can you say about, can you recognize it? Can you find out, distinguish it? See, you can. Why? Because if it were in this state, 0 state, this is an eigenstate 0, so it just cannot come out of this, make this eigenstate 1. It has to, I mean, you have seen that this is definition of eigenstate, that if I put an eigenstate into the measurement apparatus of the corresponding observable, then it has to come out as this, in the same eigenstate. It cannot come out in any other eigenstate.
Can we rephrase so as to understand? I'm just trying to understand. What was the original? You have two.
Yeah, you have to. I have a particle.
You have a particle.
I tell you that this particle is either in this state, some arbitrary state, or in eigenstate get 0.
So you don't know which state it is. But
Yeah.
one of the states you know that it's an eigenstate, say 0.
No,
You don't
no,
know
you know both the states. I am telling you that this particle is in this state. I tell you the state, or in this state. Both states are told to you. It is in one of the two states.
Even the dot state I know what.
Yeah, you know it.
It's an eigenstate or it's not an eigenstate.
It's not an eigenstate. It's an arbitrary.
But the right one is an eigenstate.
Right one is an
So
eigenstate.
one of them has to be an eigenstate.
Yeah,
The
the other is
may or may not be.
Yeah,
You don't know.
yeah, you don't know. You don't know. You know it. I am telling you the state.
If I know it, then what is the question being asked?
Why? The question is.
I don't know which state it is.
I know, I describe fully this state. What is this state? I tell you the description of this state. I tell you the description of this state. Okay. And then I tell you that this particle is in one of these two states. You want to find out of these two states, in which state?
दोन पात्रात
कुठे आहे? त्या दोन मध्ये तो कुठे आहे?
And one is eigenstate.
And one of them is eigenstate. Okay.
one
No.
of them is eigenstate
Yeah.
is a condition.
Yeah. So if I put it here, the condition means this is the situation. Yeah.
Actually, if it comes out of the one state, then you definitely know that it is in dot state.
Yeah, that is right. You don't. That is right. Exactly. If it comes out of the one state, then I know that it has to be in the dot state. It just cannot come out in the 0 state. If it were in 0 state, it would. Zero is an eigenstate, so it has to come out in 0 state. That's it.
Yeah, we can rephrase it. If
Yeah.
it is in eigenspace, the thing will change. It will come as it is. If it is not,
If it is not,
if it changes,
if it
not.
changes, yes. And then, yeah, okay. So then, but now if it comes out of this, then you don't know. Because there is a non-zero probability. Even if it was in dot state, there is some non-zero probability of this being coming out of this channel. If it were in 0 state, it would come anyway. So you don't know. So this is not a reliably distinguishable.
This is important.
But now suppose this was another eigenstate. So I tell you, I give you this particle to you and tell you that this is in either this eigenstate or that eigenstate. Both are eigenstates. Then you make a measurement and you find out. I mean, that's finished. There is no, I mean, you just find out which channel it is coming out. If it is coming out of zero channel, it is in zero state. If it is coming out in one channel, it is in one
Then they
state.
are perfectly distinguishable.
So they are reliably distinguishable, perfectly distinguishable.
It is.
Yeah.
Just to clarify, when you went to measurement, you are not making one measurement.
I am making one measurement.
So I suppose the dot state is half-half.
Huh. Huh. No, no.
So
this-
suppose the dot state is half of 1 plus half of
Huh.
0.
Oh.
So linear combination.
So, yeah.
So there is a probability that it will be in 0 or 1 when you make a measurement.
Oh.
So it could be 1, it could be 0.
Yes.
So when you say 1, how can you say it is not a linear combination?
No, no, it's not. I am not never said that it's not a linear combination.
So if it goes to 1, you are saying that it is definitely in one state. That is correct.
Ah.
No, it is
Understood.
definitely
In dot state.
It is definitely in dot state.
It's definitely in dot state.
Done.
Okay, fine. So, but two, if I get any two eigenstates, they are always reliably distinguishable.
एक तो डालेंगे तो
So,
एक
and we have seen that they form a basis and they form a orthonormal basis. In fact, I have made that statement. And they also form a distinguishable basis. This is called a distinguishable basis, that any two of them can be distinguished. Now, suppose I have two states, or say psi and phi. Again, a particle is given to you and you are told that it is in one of these two states. You don't know which. Okay? Now what I can do is, I can construct an orthonormal basis which contains psi, which is always possible. For any normalized state, give me any normalized state, I can construct an orthonormal basis which contains that state. Because you have to put, you have to choose linearly independent states and orthonormalize them. I am not going in that, but you can always construct. So given an orthonormal basis, I construct, there is an observable, say whatever sigma or whatever, of which this is you can make a measurement to that basis. Measuring to that basis means you are measuring the observable whose eigenbasis is that basis. So if I make that observable measurement, there may be many. I am drawing like this because here only two possibilities were there. Here in general, I put this psi. Okay. Now I am told something more, that these are distinguishable. You are given this information. These are distinguishable. That means, suppose this is the channel for psi. Now psi is an eigenstate, okay, of the observable whose eigenbasis is that basis which contains psi. Let me go slow. Have you understood this?
I thought you can get psi in terms of
linear com-
orthonormal basis.
No. I am constructing a basis, orthonormal basis, which contains a psi, and I am making a measurement to that basis.
So psi can
But
be
the
written as a
size
linear
is expanded in terms of that orthonormal.
I am not expanding anything.
Contains psi means what?
Basis contains psi. Psi is a member of that basis. Ket psi is a member of that basis.
One of the
eigenstates, one of the states.
eigenstates.
Yeah.
That's psi is one of the eigenstates.
phi belong to the basis.
Psi belongs to that basis. I am making a measurement to that. Okay. Now I have already told you that you know that the particle is in one of the states, ket psi or ket phi. Some additional information I give you, that these are distinguishable. Okay. That means what? That means if I have now make a measurement on phi, since phi and psi are distinguishable, the particle in state phi cannot go through the psi channel. When that will happen? That will happen when the probability when I expand this phi in terms of the psi basis, that is superposition using the psi basis of phi, okay, what is the amplitude corresponding coefficient? Coefficient is, okay, and probability is this.
Are the elements of same basis, sir?
No. Phi is some state. Psi, I am constructing a basis which contains psi. Psi is a member of that big basis.
Phi.
Phi is not. Phi could not. Okay. So that means this has to be 0. The probability that phi will, particle in state phi will go through the psi channel, it has to be 0. Because if it were in phi state and still goes through the psi channel, distinguishability is destroyed. I cannot distinguish them. So that probability has to be 0. But then what does it mean? It means that scalar product phi psi has to be 0. That means phi and psi have to be orthogonal in this case. Now reverse it. What I will do is, now there are two states, particle, possibly in two states, one of the two states, I don't know which, but it is in one of the two states. And then I tell you that these states are orthogonal. Then it is easy to show that they must be distinguishable, because now again I do the same thing. I construct a basis containing psi and make a measurement to it. Okay. Now these are orthogonal. That means this probability is 0. That means they are distinguishable.
So you are proving if and only
If and only, both. So orthonormality I say because in this course we will always deal with normalized states. We forget about states which are not normalized. Don't worry about that. Therefore, orthogonality and orthonormality for me is the same thing. Okay. So distinguishable basis and orthonormal basis are the same. Is distinguishability and orthonormality is they are the same concept. Okay. Each implies the other. Okay. See, distinguishability is an important concept in quantum computing. We will see that when we come to some applications. Okay. So now let us see.
So can we say this statement, distinguishability in the context of quantum,
Distinguishability of states, quantum states.
in terms of quantum, is equivalent to saying orthonormality in the context of vectors, state vectors.
See, we are staying only on quantum states. We don't. Vectors is a nomenclature. You are calling these states as vectors because in general vector space mathematical construction which you call vector space or linear space, the elements of that space you are calling vectors.
Even if we don't have the concept of vector space, we can pull the concept of distinguishability.
No. You need, because I am dealing with a basis. I am constructing a basis.
Once we say that both are orthogonality is same as
the quantum states, total collection of quantum states of a quantum system forms a linear space. Forms a vector space. Is that clear? They form a vector space. That means, now what is the mathematical description? What are the basic characteristics of a vector space as we did it yesterday? That first fundamental definition is linear combination. For linear combination you need coefficients. Those coefficients form the scalar, set of scalars. Here it is.
What was his question?
His question is,
the question is, one can call upon this concept of distinguishability. Just one thing is distinguishable to other. We don't need a vector space for that. But once we prove that distinguishability implies orthogonality and orthogonality.
May I know your name? Amit. See, Amit, while proving this, we essentially used an assumption which is apart from your vector space. What is that assumption? It is assumption about quantum mechanics, quantum systems, and that assumption is if I have an eigenstate and if I measure that corresponding variable or that observable on that eigenstate, then nothing changes. No, this assumption doesn't follow from vector space. This is an additional assumption and it is being crucially used. So we are talking about quantum systems. We are not talking about, I mean, what you want to say is that all this can be lifted to a general vector space. No.
No.
That's not.
My question was,
Let's say whether his statement is right or wrong, or it has to be augmented. That's why I'm trying to get his statement. It's either right or wrong, or it has to be clarified or augmented.
maybe we'll discuss after.
Yeah, maybe.
Yeah, that's okay, fine. So, but it is clear, what I am saying is clear, there is no problem, okay, about anybody, it's no problem, okay. So, okay, now let us go over and consider some operators. See, I have already told you that any change in state, going from this state to that state, is in the quantum mechanics model is an action of an operator on the state space. State space is the space of states. Okay. So now, yeah. So we are already Dr. Canary and so, for example, the most famous thing is Hamiltonian acting on some En. This is your time-independent Schrodinger equation. So that's an eigenvalue equation. So this is the eigenvalue equation, which, I mean, I assume that you have come in contact with these kinds of equations, and you know. In fact, most probably you have used matrices to do it, but that equivalently you can do it here also. I'm not going into that. So this is your now this operator which satisfies. So now I find out, I mean, mathematically I find out what are the list of all the eigenstates of this and the list of all possible eigenvalues of this, solving this equation. Okay, that means this operator corresponds to some observable. It is breeding out the eigenvalues and the eigenstates. Okay, I mean, you have a matrix and you diagonalize it, you know, this is exactly the same thing. You can use an operator algebra also to do it, but we are not doing it here. So this is your equation. So what conditions does it imply on this operator A? See, we have seen that all eigenvalues must be real and all eigenstates must be either distinguishable or orthogonal. Of course, I mean, all eigenstates with distinct eigenvalues. So this operator must satisfy this condition mathematically. All its eigenstates which I get by solving this equation must be orthogonal, belonging to different eigenvalues must be orthogonal, and all its eigenvalues must be real. So this the operator which satisfies these two conditions is called Hermitian. Okay. So in order to mathematically specify the hermiticity, we have to first define what is called an adjoint. Adjoint of an operator, and given an operator A, its adjoint is denoted by A dagger. Now you can take, I mean, more rigorous definitions can be used, but operationally, I mean, since you are engineers, you know, your more operational thing is more important for you. So operationally, I take this ket. This is a ket. Why? Because when U is a ket, some state, I act by operator A on U, I get some other ket. I mean, that is what that operator is doing. It is acting on some ket to give you some other ket. It is kind of development of that operator, that state. So this is the kit. The question is, what is the bra corresponding to this kit? The bra is, this is operational definition of this operator, adjoint operator. Okay? So bra corresponding to, given a kit linear operator A, I make it act on some state, normalized state U, I get some other state. The question is, what is the bra corresponding to this state? Okay? So the answer is this. So now consider, say, X, A dagger, Y. That is, suppose I made it like this. This is your bra and Y is this. So this is a scalar product. This is a bra and kit Y. This is a scalar product. But I know this is include. This is a condition has to be satisfied by all scalar products. So that means the role of Y is being played by this A dagger acting on bra X. So here I must get the corresponding kit. The corresponding kit is A, Y. And this, AX, sorry, here, AX. And the corresponding bra for Y is, and I must have this star. That's it. So this is a fundamental property, a useful property of A dagger, or this adjoint, which is used. So now suppose, okay, let me this is not that thing. Consider this arbitrary state X, A dagger, dagger, Y. That is equal to, I leave it for you to understand this. This is A dagger. I interchange this X star and again apply the same rule. I will get X, A, Y. I am using just this, nothing more. Do it yourself instead of me explaining it. It's the same thing. Okay. So it just means that, and since X and Y are arbitrary, this just means that A dagger, dagger equal to A. Okay. The next important property is, if I take some C A dagger. Now in your discussion, active learning, you will prove that the bra corresponding to C phi is C star bra phi. Okay, that you will prove. Okay. So now here, if I use this C A dagger, X, Y, that is equal to, now this is C multiplying your bra, you have to take the star of it, so that is star, C star will come out, Y, A, X star, that is equal to C star, X, A dagger, Y. So that means C A dagger equal to C star. And the last thing is, you consider this X, B dagger, A dagger, Y equal to, now see this A dagger, I'm using this property here for this A dagger, so I'll get Y, then A, and then what is the kate corresponding to this? This is just B X. Yes. Is it? It is. So this is equal to X AB dagger Y. See, first I will suppose. What I am doing is I have X. X. Oh, yeah, of course. I'm sorry. Start. So, so here, this Y AB X star corresponds to X AB dagger Y, where AB is taken to be as one operator, one operation. Okay. So that is the thing. So that means, what does it mean? AB dagger equal to B dagger, A dagger. Go through this.
One of the simple ways is to understand that if you take these as matrices, all this is but matrices are very specific and he is making it very general because this works everywhere. Matrices will work on only matrices.
That's
but
right.
it's the same. Complex conjugate and transpose, that's all what it is.
Yeah, that's it.
So you
Yeah,
do
that's
that and then you will get everything.
Then I'm assuming that the matrices part you already know. Otherwise, if I include that, then it will
This is told we are able to relate very strongly.
go. Otherwise, it will go on like this. Okay. So, C is a number, complex number. Complex number. So I have C. Say I have an operator A. I multiply it by complex number C. It becomes another operator. Say if I take U as a kate, I operate by CA, means I operate by A, I will get some kate, and C will again multiply to that kate. That's it.
General concept of transpose. General concept.
No. These are the things which are possibly can be you may be encountering in this.
When we discuss transpose operator, we discuss this.
No. So see, this is nothing to do with transpose of a matrix or anything like that. I am just multiplying by a complex number. That's it, nothing more. Okay. C star is the complex conjugate. Star means conjugate. Yeah. There seems to be some fundamental misconnections. Please remember that star means complex conjugate. I take any say scalar product which is a complex number. If I put a star on it, that means it's a complex conjugate of that. Is that clear? You?
So this fundamental concept we understood with the help of this equation. But can you discuss this fundamental in terms of application?
I am going to do that. But there are your
Because these equations become heavy for us. So instead of this equation, if you explain in terms of any application or any
Actually-
example of engineering.
Actually, sir, what he is doing, Hamiltonian define करना है. We need to define Hamiltonian. Means or symmetric operator. A Hermitian I. So from where that Hermitian or this comes with the help of dual space, he is trying to explain.
see, for example, measurement. We are talking about measurement. Measurement is an absolutely essential part of computing.
Counter application.
Yeah, because you compute using a quantum circuit, output of that circuit is some state. All quantum information is contained in a quantum state, like this gate psi or whatever that is. Okay, you want to bring that information to your world, what you can see and work with it. How do you do it? You have to make a measurement. So the output device of a quantum computer is always
Is a measurement.
measurement. So measurement is extremely important. So you have to know what that measurement means, what it can do, what it cannot do, and so on. Okay. You have to know what is linear independence, what is a basis, and what is all these kinds of. You have to know that eigenstates of an observable forms an orthonormal basis and things like that. You will be using it in superposition. You will be using this expression. See, this expression that we derived, this is the probability, okay, in that expansion. This is the probability that, I will have to do it again, so, okay, fine, K psi. So psi is being expressed as a superposition of these basis states. This is the superposition. Coefficients are like this. We have proved that. We first wrote that it is summation over K, C, K, K. So K is some K0, K1, K3, K4. This is the basis. Okay? And this is Ck into that. So C0, 0 plus C1, 1 plus C2, 2, like this. Until the end of the basis, all basis states. Now we proved that this C1, C0, C1, etc. are like this, provided the basis is orthonormal. It's not true for arbitrary basis. You see the connection. And then we prove that the eigenbasis of a for measurable quantity, that is the observable, if I make a measurement on this K psi of that observable whose basis is this K, then the probability that I will get, say, nth state as a result of measurement is this. This probability is this. This you have to know.
There is some difficulty.
If you see, can you appreciate that if you don't know this,
I appreciate
what kind of quantum computation you are going to do? You will not understand what is happening. You appreciate this point. Okay.
Or you can think like that. If your student asks tomorrow, sir, how your measurement operator is working, why it is giving this result, so how will you explain? So these things will be required. Yes.
So you should know what measurement is all about, its
Yeah,
characteristics,
to
what is
convince them,
orthonormality and things like that.
We will
And
need this. Otherwise, we will not be able to answer this question today.
there is not a question of answering students, that comes later. You have to first understand yourself.
That is a very practical. You have to understand. That is practical.
So, मुझे पागल कुत्ते ने काटा नहीं है.
नहीं. He's not saying. No, sir. You will appreciate maybe after once we.
Yeah, once you get into that, you will appreciate all these things.
It takes
बुरा
some-
लागतं ते बुरा लागायला थोडा वेळ लागतो.
बॅकग्राऊंड चाललेलं आहे त्या बॅकग्राऊंड शिवाय पुढची स्टेप उडी मारल्यासारखी.
No, sir. You will.
Now we'll go over to very important operator. It's called unitary operator. We have dealt with Hermitian operator, but now let's go over to unitary operator. Unitary operator is defined by the equation that it preserves the scalar product. See, unitary operator U, when it acts on Y, okay, what it is, and Y is, forget about this. Suppose it acts on X, okay, then what is its bra? So you have two states, U on X and U on Y, and I want to find out the scalar product of it. That means I have to take the bra of this, and this is the ket. So you have X, U dagger, this is the bra of this, UY. And if this was unitary, if this operator was unitary, then this satisfies this equation, that the value of these two scalar products are the same. Now, why it is important? It preserves the scalar products. Why is it important? It is important because it preserves normalization. Normalization is important. If it is not normalized, then this mod square of the coefficients cannot be treated as probabilities because they are not adding up to 1. That is no normalization. Okay? But I want an operator for the development of a Kate, normalized Kate, so that the resulting Kate must also be normalized. You can just get in a Kate which is not normalized, and so the probability interpretation is not available for that Kate. So, for example, psi is your Kate. You operate by u, you get u psi, and now I construct this. This is the bra corresponding to u psi. So I construct this psi, u dagger u psi. This is equal to psi. And if psi was normalized, this is equal to 1. So that means okay. So it also preserves norm. That is, of course, I mean, this we have seen that this is norm square. I have already yesterday defined it. You just check that. See, there is one more point. You must sit with your notes of the lecture and try to work it out. This is the Feynman way. I mean, the next step is the Feynman way. Feynman attended the course given by Wheeler, John Archibald Wheeler. Okay, and all people were quite smart there. They used to keep on writing, but Wheeler used to write or say. Feynman used to just listen and used to write whatever he needs. I mean, he decides what he wants. That's it. And then he goes home and reconstructs the whole lecture. It's the Feynman way. Okay, so I mean, I'm not saying that, but try to reconstruct the lecture. I mean, to whatever extent. Yeah. त्याच्याशिवाय येणार नाही ते. येणार नाही. Okay. So yeah. So this is the thing. So this preserves your norm. Another property of useful property is the eigenvalue. So consider this eigenvalue equation for a unitary operator. We take the bra of it, that means u we have already seen that lambda into u, the corresponding bra is lambda star u. Now see, take the corresponding scalar products for both the equations. So you will get here u scalar. By definition of the unitarity, this first equality follows. Scalar product of u with itself is equal to u dagger u. That is equal to scalar product of this part is mod lambda square, lambda into lambda star mod lambda square u. So I get u, that is this scalar product of u with itself is equal to mod lambda square into the same thing. That means mod lambda square equal to 1. That means lambda has to be the form e raised to alpha. Lambda is a complex number, so I can write this complex number as lambda. I can write this as mod lambda into e raised to alpha. Polar representation for complex number. But I know that now I have proved that mod lambda is 1. So the eigenvalue of a unitary operator is complex. I mean, e raised to alpha. It's a phase. Okay, so that's what. Okay, we have done Hermitian operators. So now what else? Just let me see. So let us do projection operators, which are extremely important. Just elementary exposition of projection operators. So projection operator corresponding to a state alpha is written like this, and its action on some arbitrary state psi is given by this is exactly like projection of a vector on some other vector. So suppose you have this vector, this is unit vector I, okay, and this is some vector. If I project it, what do I get? Suppose A, I get A dot I into I. I get this. I project this psi into state alpha, onto state alpha. That's what is happening. I am projecting the state psi, ket psi, onto state ket alpha. So just like this, I must get the scalar product of this alpha and psi and ket alpha out. This is the projection operator. Okay. Now there is a generalization of this, which is what is called outer product operator. What is the outer product operator? It is, I'm sorry, now the most important thing to realize in practice is I can use this equation in both ways. That is, if I get an expression like this, I can replace it by the operator like this, action of operator like this. If I get an operator like this, left hand side like this, then I can replace it by right hand side. Both ways, you will have occasions to use this equation both ways. Okay, sorry. So, okay, so so let me do this. So you'll try to follow. Phi, this is phi, this is phi, so this is psi. Now this operates according to this definition. This will give me psi beta star alpha psi star. Okay, is it okay? Is that okay? Use the definition. This is the definition. This definition I am using. Action of this operator on phi. This will give me this. And what is happening here? I am psi phi. This should be phi here. Sorry. So that will give me phi alpha. Scalar product phi alpha into beta. So the result of this is beta Huh? This is an operator. This is an operator. Yep. This is an operator which is operating on arbitrary state ket psi. The result is beta into the scalar product of alpha and psi. This is the definition of outer product operator. I am defining that operator. I mean, it's not. Yeah, beta becomes, it brings out beta state and with a multiplied by the scalar product of them. It's a generalization of your projector. Projector is when you replace beta by alpha. So you get alpha alpha on this. The same way. Now you have beta alpha like this. So I have beta alpha here operating on this. That this will give me beta into alpha phi star. Now this beta combines with this psi. So I'll get this gives me this.
Operating on psi
No, only I am circling that, na. Whatever is inside the circle gives me this.
operator should always be left.
No. There is no operator here. It's a ket beta into this scalar complex number. It's just ket beta. This is state and this is a complex number. Nothing more. Okay. But now you replace it here. This is replaced by this here. Then I get bra psi ket beta. That will give me a scalar product here.
States are what?
Huh?
States are what?
Only two complex numbers will. Yeah, that's it. Okay. So that is equal to phi alpha into beta psi, because कुठलं हे हा ऑपरेटर आहे, हे हा डॅगर आहे. तर डॅगरचं तुम्ही हे केलं तर काय होईल, नाही वी हॅव सीन दिस. तू गेलं हे, सो त्याच्यावरनं हा डॅगर गेला आणि हे उलट झालं स्टार. ओके. त्याच आता हा ऑपरेटर याच्यावर टाकला, हे येणार जस्ट सर्कल. या सर्कलमध्ये काय आहे, हा ऑपरेटर ऍक्टिंग ऑन दिस फाय. दॅट विल गिव्ह मी केट बीटा इंटू दिस कॉम्प्लेक्स नंबर विच इज स्टार. न केट बीटा, आता हा ब्रा इथे आणून ठेवा. So this one, and now हे उलट केलं की हा स्टार जातो. And now this I use this again in the reverse order. So I get now, what do I get here? No. Phi alpha beta psi. So I get psi. So this is equal to, I will explain that. Phi So how does this follow this? I use it in the reverse order. Beta into this scalar product is the same as operator beta alpha on psi. See, this take only this, so you will get this is beta alpha on psi. The same equation in the reversal. So what does it mean? It means that phi, this dagger psi is phi, this into psi. So it means that alpha, what is this? Beta alpha dagger equal to alpha beta. So you take the dagger of the outer product alpha, beta alpha, you get the outer product reversed. So immediately it follows that if you put beta equal to alpha, then alpha dagger equal to alpha. Because beta is replaced by alpha there. Beta is replaced by alpha. So what does it mean? What does it mean? I want you to answer this. Alpha dagger equal to alpha means what? Means what? What can you say about this operator? Projection. Sangha Mrs. Sore. Not unitary. Huh? This is a projection operator. This equation, what does it mean? Hermitian. So this projection operator is Hermitian. Projection operator is Hermitian operator. Okay. So, okay, fine. So, now a very important thing that I think then I will go over to something else. Look here. Some arbitrary state psi that is equal to summation over k into bracket k psi. We have derived this. K is an orthogonal basis. So this is okay. No problem. This I can write using this equation. I use this equation. I have k psi, right hand side. I replace it by left hand side. In each term I use this equation and replace it by left hand side. So this is equal to summation over k yeah, see, look at this. You will not understand. If you just keep on looking here, you will not understand anything. You have to look at this equation, and then you look here. I get k into this scalar product. I am getting k alpha into this scalar product. Though it is the same. It is the right hand side of this equation there. So I replace it by left hand side. And this happens in each term. Each term you will get this. So that means I will get this. Do you agree? You agree? Everybody, one who disagrees will discuss it. What about you? Do you understand or no? No? Why? Look at this. This is the equation, you see. This is the definition of the projection operator. I get k alpha into bracket alpha psi. Here I get k into bracket k psi. That means it is identical with this right hand side, no? So I can replace it by its equality. I can replace it by left hand side. What is that left hand side? Here alpha is replaced by k. So projection operator k
प्रत्येक term.
And that is in every term. K is a running index. You get it? Okay. That means this equation. So I get ket psi equal to this operating on ket psi. So I am getting ket psi back. So what does it mean? It means that this is an identity operator. Identity operator is operator which does nothing. An identity operator acting on any ket will give me the same ket. That's it. This is called resolution of identity, and it is extremely useful. You will be using it in every time. Let me give an example. Like this, suppose I want a observable A average value. By definition it is, I am using discrete thing. So summation over I, lambda I, Pi. What is Pi? Pi is the probability for lambda. This is the definition of average. Take the value, replace, multiply it by its corresponding probability and sum over all values. That is by definition the average. Okay, so now this summation over I, lambda I psi square. Okay, so that is equal to, that I can write as summation over I, lambda I psi, lambda I to psi. So this is mod square. I am writing it as a mod z square is z star into z. So what is the z star of it? Reverse the order. This into this. That's it. Is it clear? Okay. So हाँ 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 नहीं पहला psi okay sorry psi okay. Now I will take this lambda here. This lambda, if I take multiply, so this lambda into psi, I can write it as operation of A on psi. So this is equal to summation of I psi lambda I sorry A psi, because lambda I into lambda into lambda ket lambda I is so I can write it different. Lambda I into lambda ket lambda I is just A into ket lambda, A operating on ket lambda I. So this is psi A lambda I psi. This I can write as psi into bracket summation over I lambda I psi. What can you say about this summation over I projector lambda I lambda I?
You missed the A.
Huh? Oh, A. Sorry. A. Sorry. What can you say about this? Just now we have done it. What is lambda I? Lambda is an eigenbasis. It's orthogonal basis. So this is identity. Okay. So that will give me psi A psi. So this is the average value of operator A in state psi. So this is one example how this comes in handy, this identity, resolution of identity. Okay. So now what next? Okay, so this is I have to leave it alone. Let me not do this at the moment. I will just. Okay, so now I will stop doing this at the moment. We will pick up something, small things when as and when required. What is now, what is now left is to define measurement operators and all that. But let me, we will do it later. Okay. So now I want to answer one question. Let me write that question here. We start with this question. This is the question. So suppose two quantum particles individually have states, Hilbert spaces, state spaces individually. Have Hilbert spaces H1 and H2. These are the state spaces for each particle. Okay. So the question is this. What is the state space of the composite system? How to specify the states of such composite system and operators acting on it. How to specify these states? States are just like states of composite systems. How to specify them and operators acting. How to specify the operators? Acting on them. More than two, three particles are there. Each particle has its own state space. What is the combined state space? How do you specify these states? Again, a fundamental question for quantum computing. So let us start by showing that these two particles are so far apart that they are not interacting at all. So large separation that they are not interacting at all. Now this consider an observable A on this and an observable B on this. Particles are far apart. I measure A on that particle, one particle corresponding to state space H1. So what will happen? What are the possible results? The results are, these are the eigenbases of A and up to say M. Because the dimension of the Hilbert space of the first particle is M. So the basis will contain M elements. Okay. And I measure B, whose eigenbasis is again N. Because the dimension of H2 is n. That means the basis contains n elements. Okay. So how can I can very simply specify the combined states like 0, 0 or 0, 1. So this 0 is combined with all this n, 0, 0, 0, 1, 0, 2, 0, 3 up to 0 n. That make n. Then 1, 1, 0, 1, 1 up to 1 n. All ordered pairs. How many of them are there? M into n. So this gives me the proof that whatever combined Hilbert space I can construct of these two particles together must have dimension m into n, because this forms a combined basis of this. Both are eigenbases. Okay, and therefore the ordered pairs should correspond to the basis. And it contains m into n elements, and therefore the dimension must be m into n. Okay. But now, I mean, this doesn't construct the Hilbert space of the combined system. Okay. And another observation is that once I get this basis, this kind of basis, and I need to generate the actual basis out of these ordered pairs. But the basis generated out of these ordered pairs can be used to express any arbitrary state of these two particles when they are interacting. It doesn't matter. As a superposition of the basis states, that's the definition of the basis. Okay. No problem. Okay. Now we have to construct that basis. So how will you do that? What I want is this. Now these are separated. I mean they are separated. They are not interacting. Okay. So the linearity of the individual Hilbert spaces must be preserved. Okay. So I mean they are not interacting. So I must be able to treat one separately and the other thing separately. I mean I am not compelled to combine them and treat them as a combined system. Right? Huh? So linearity in each case must be preserved. That makes it that necessitates me to have a bilinear map such that linearity of every thing is preserved. So bilinear map is CB KU plus KV in the first case in H1, comma KW in H2. So this is the pair. This is B is the bilinear map which operates on this pair. That should give me B U W or U omega or UW plus B VW. Okay. So this is the, I mean, so this linearity, I am not multiplying by alpha 1, alpha 2, etc. But this linearity goes to individual cases. And similarly, if you have U and V plus W, you will get B UV plus B UW. Similarly, now you have to multiply by. Can I write here now? I think I am writing here. Okay. Is it okay? So B alpha U comma V is equal to alpha B I'm sorry. So this is equal to B U alpha v, and that is equal to alpha b u. So this is the definition of a bilinear map. So I must have a bilinear map which maps this pair of state spaces H1 and H2 into a combined space like this. So I have a product state, I mean this state where it consists of all ordered pairs, and from that I want this bilinear map to give you, so I want a map phi which will take H1 into H2. These are the set of ordered pairs to some, or it maps it to some state space T, linear space T. And this map has to satisfy following three conditions. So which follow from this, but I will write them. What are these three conditions? This map P1 bilinearity. This is map B must be bilinear. T2 is, I mean this phi H1 into H2 is equal to T. That is, I mean this phi should map every element in H1 into H2 into some element of T. So it's a complete map. And this T3 is if k equal to 1 to up to m, and L equal to 1 to up to n. Are bases in H1 and H2 respectively, then phi k l k running from 1 to m, L running from 1 to n is a basis in the combined space. So this is how the combined space is constructed, and that first thing that we note that this dimension of the combined space is the product of the dimensions of the component spaces, and these are the we have to connect just the space of ordered pairs to the linear space which can combine arbitrary states of a combined system and give you a new element of the same space. So for that I need a bilinear map which satisfies these three conditions. But that is not the end of the story, because what can happen is I can have another map. See. I can have another map, that phi prime, which will map H1 to say T prime, which satisfies all these three conditions. then I have a problem. Because then my combined space is ill-defined. I mean, I don't know whether to use this T prime or T. But there is a theorem which saves us. This theorem is the following, that the statement of this theorem. Suppose there are two such maps, phi prime, phi and phi prime, which satisfy all these three conditions, which map this product space to this space T. Then there exists an invertible map tau between, let me state. Then we can find a unique invertible map tau which will take from T to T prime and which is an isomorphism. I will come to that. I will come to this. So there is a unique invertible map from T to T prime and which is an isomorphism. So that means, I mean, what is isomorphism is this, that suppose you have two sets, you have two sets, say S and T or whatever that is. There are two sets, and S has a binary operation 0 and this has a binary operation multiplication, whatever that binary symbol. Then a map which takes S to T is called a homomorphism if map phi which takes some A circle B to phi A so you take two elements of S and they combine by circle operation. I will get some other element of S. Then what I will do is I will apply phi, take A to its image, take B to its image, and combine by multiplying this cross operation on the other set. I get the result, which is again a homomorphic image of that result of the first operation and the second operation. They are homomorphic images. Okay. And if this map is 1-to-1 and onto, then it is called isomorphism. So if two sets and these kinds of things are there, and if there is an isomorphism between them, then you need only one set. You need to select only one set. Because the other set corresponding images are following the same pattern, same result. If I know that A circle B is C, then I automatically know that phi A cross phi B is equal to phi C. So I don't have to. One of my mathematician friends used to describe one very famous cinema actor in Tamil Nadu. He used to say that all his films are isomorphic. I mean, this only the actors and actresses change and all that. That's all. And there is a deviation from isomorphism for in his films in the last year of his power. He was the chief minister also, fifth year. So, for example, there will be a shot in which this person is touching the feet of an elderly Tamil woman. So that assures him the votes of all menopause women. So, and there are 4 or 5 shots like this, and he's straight back to power. That's it. Finish. So, I mean, this is an example of isomorphism. In practice, this is and we'll see that many Hindi movies also, you'll see that they are isomorphic, many of them, essentially. So this is an isomorphism. So that means which phi I am using is not important. I can use different phi satisfying the same 3 conditions. Okay, I can use phi mapping with the same 3 conditions, which is invertible, which are connected by invertible and isomorphic map is.
Sir, I thought that the condition B2,
Uh,
is it not something
no, this is a onto condition. I mean, yeah. So this condition says that this, I mean, it should not happen that the image of some element of this ordered pair is simply not in T. That should not happen.
but it is not one.
No. There is no. It is 1-1 because I mean this tau is 1-1. Tau map is 1-1. 1-1 because it is invertible. Unless it is 1-1, it will not be invertible.
Now, what I was thinking that if, so when we are looking at condition D2,
Ah.
so why is it not considered 1-1 also? Because then this would have been invertible, it would have been unique.
No, this is not a unique. I am finding out totally different. There is no restriction. I can find out some different, totally different map. This phi prime. There is no relation between phi and phi prime. Apart from the fact that both satisfy these three. That's it. That will be in different spaces, no? So that is my problem. Yeah, but this theorem says me because this is isomorphic, and therefore it doesn't matter which phi I am using. Because I choose one phi and I construct one space, it is enough to study that space. Because other space is an isomorphic image. So there is nothing. And therefore you can what you can do is you have some U in H1 and V in H2. I can write it as U tensor V. This is called the tensor product. This T or this bilinear map, the state space I get using this bilinear map is called a tensor product of two spaces, H1, H2. So this is written as H1 tensor H2. This space is written as and any element again is written as this. But this always, I mean, since we are lazy, we will always, and it may be cumbersome also. So we may not write it like this. We may write it just UV when the context is clear, or you just maybe write UV. I mean, this is the condensed way of writing the tensor product. So, for example, if you have two state systems with basis 1, 0, 1 and again 0, 1, then I can write 0, 0, 0, 1, 1, 0, 1. These are actually, this 0, 0 is actually Ket 0 tensor Ket 0. This is Ket 0 Ket tensor Ket 1. This is Ket 1 tensor Ket 0. And this is Ket 1 tensor Ket 2. Actually. But I am writing like this. This is convenient. Because I can view it as a binary string. Okay, so what else? Are you tired? Or yeah. What is the time? Huh? 11:30. So fine. We are done. Okay. Thank you so much. So in fact, I promised Kunj that I will discuss some circuit, but now I don't think it's already 11:30. Duparun, the wait minute, I think 2 lectures have. Anjali is talking and Dilip is also talking. So I don't know whether if I get time, we will discuss the circuit. हाँ तर मग तेव्हा मी एखादं सर्किट डिस्कस करेन. चला चहा पिऊया.
Okay, so what we are going to do is, I will repeat some of the things that we discussed about quantum mechanics, whatever we have discussed in last 2-3 lectures, and then many of the things that I wanted to do have been covered, but I will just repeat, like how do we define an Hermitian operator, what are the properties of the corresponding eigenvalues, eigenfunctions and so on. And basically I am going to describe or work out the one problem, that is particle in an infinite well. And then I was also thinking of expanding any general function in terms of this, so that how you use the eigenfunctions to represent the general state. So that is what I plan to do in this, and so if we are not able to finish everything by one, I will come back and continue. So we have discussed that psi of x is the state of a quantum particle at any instant of time, and it does not have directly any physical representation, but what we have is this psi of xt mod square dx. It represents the probability of finding the particle between x and x plus dx. That is what we have discussed. This is also, we are generally referring to this as probability density, but more exactly it will be position probability density. And in analogy with what you normally use in classical electromagnetic theory, you write intensity as amplitude square. Therefore, here we call this as the probability amplitude. Okay. And since the probability of finding, and again as Kanere sir had told many times, that currently we are talking only about a single particle. So we are talking about a system which contains only one particle. It can be an electron, for example. So probability of finding the particle somewhere in space, and we are also talking about a particle in one-dimensional space. So it is only a function of x and of course time. So what we are saying is this probability, when integrated over whole space, has to be 1. That means this wave function has to be normalized, so that the total probability is 1. This is at any instant of time t. Now the question is, if the potential is not dependent on time, will this be conserved? Like at any other time, will you have the same probability? Okay? And we have not yet defined, and we may not use it very often, but I would also like to describe or define a quantity which we call as the probability current density. Function of x and t. And they satisfy the continuity equation, that is, so this I can say this I can call as rho of xt. So dabba by dabba t of rho xt plus so these are some of the things which, so except for this probability current density, we had defined the things more or less earlier. So I had a few questions. What do you think will be the dimensions of psi of x and dimensions of mod psi square? So if you think, you can give an answer just now, otherwise you think about it.
It's a good active learning.
Yeah.
Let's maybe take a pause.
Okay.
It would be good. It's good.
No, that's right. I mean, this is not an engineering question, but this is a physics question. But you all deal with dimensions much more than what we deal because you are more practical. So when she's saying that what are the dimensions in terms of L, M, and T and whatever, it's just to pick up the fine points of physics which are reflected there. So it's a good active point. Yes. So mod psi square.
So you have certain equations written here.
So what would be the dimension of mod of psi square?
Look at this. Mod psi square dx gives you a number, isn't it? It's 1. So, and dx is what? It's length. So if this is a number, this has to be a number. So this has to be having a dimension 1 upon L. So psi has a dimension of 1 upon root L in 1 dimensions. If you go to 3 dimensions, corresponding integral would be this is a volume element in 3D, and this is again a number. So sorry. So here mod psi square would be having dimensions of 1 upon volume. So psi would be 1 upon L raised to 3 by 2.
What do you mean by dimensionality here? Vector space the dimension.
No, it's not the dimensionality of the vector. Dimension in the normal sense, L, M, L and T, when we say length, mass and time. Yeah.
Left side, right side का same आना चाहिए.
That dimension, not the dimension of the vector spaces. This has nothing to do with the dimension of the vector space.
That's
Physical dimensions I'm asking. Yeah.
How you
Yeah.
1 upon root E.
Yeah. Yeah. Okay, so the question, other question which I put was, if I start with some probability that at some instant of time, I am saying, sorry, some instant of time t0, the probability is 1, the system is evolving with time. Yeah, we said that this is actually, like we can separate out. What we said is if the potential is not dependent on time, we can separate the time part and the space part, maybe in 1 dimension or in 3 dimensions. And then he had showed yesterday that the time part is, so if I write the total wave function as capital psi, which is a function of x and t, I can write this as psi of x, that is only the space part, and say phi of t. If potential is not dependent on time, then I can do that. And yesterday he had shown that this goes as e to the power minus I e t upon h cross. So in general, my wave function depends on time, but if the potential is not dependent on time, then your mod psi square will not change with time.
By potential means that will go.
Mod psi square means actually the psi can evolve. Psi will be different at different positions. But with time, the total probability, if I am saying that at some instant of time the total probability of finding the particle somewhere is 1, at all times it will remain 1.
Will not change.
Huh. The wave function itself will evolve with time, but because of this, the total probability is not going to change. What will happen if the potential is dependent on time? So that I am leaving it to you.
I have a question connecting to what he said.
Yeah.
She just said that the wave function evolves in time. Normalization doesn't change. It evolves in time with e to the power of minus it upon h cross. So if I take that as an operator, what is the characteristic of that operator in the light of what we discussed? It was a joke discussed. what kind of operator is that? Is it Hermitian, it's unitary, it's normal, it has no characteristic. Normalization is preserved with time evolution. And here, he specifically in fact mentioned the last operator which preserves. So e to the power of minus it, e upon epsilon must be a unitary operator, otherwise it won't work. And that's the importance of unitary operators.
Yes.
In quantum computing. Because all that you do on the initial state when you start computing must be to change it only with unitary operators, nothing else. Of course, that part is taken care of by the hardware people, how to implement that unitary operator. But when you actually do it, all the operators will be unitary. All the gates operators will be unitary.
In terms of quantum computing.
Unitary operators. Here it's a unitary operator. That one. Exponential operator. It's modulo 1. All exponential operators are modulo 1.
And the probability conservation, to prove that probability conservation, you have to use the hermeticity of the operator. So that I said as I am going to leave it to you. He has already defined a Hermitian operator, but I would like to define in the normal way that we are used to writing integrals. So I have any two general states psi and phi. Then if I am talking about an operator O, and as we have discussed earlier, all observables in quantum mechanics are represented through some operators. So you have an operator operating on a state giving you an observable quantity. So let's say O is an operator, then if you have psi star x O operating on phi of x dx giving you O operating on psi of x star, which is complex conjugate, phi of x dx, then you say that O is a Hermitian operator. Okay, so in terms of bracket notation, we write this as psi O phi is equal to O operating on psi and integral psi star x phi x dx, which defines the inner product, we write as psi phi. So we can call it scalar product, inner product. These our states are states in an inner product space, complete inner product space. And therefore, if you have just inner product of psi with itself, that he has shown that it is mod psi square, the norm of the state psi. So in 3 dimensions, you can think of this as a length of the vector. If psi r is a vector in a normal 3 dimensional space, then this will the inner product or scalar product of r with itself will represent the length or square root of that. So basically, mod square will be length square for that vector. So likewise here we have any state psi. So inner product of psi with itself is mod psi square. This is magnitude actually, modulus square, we call it norm square. So that represents in some sense the length of the vector. And the observables we had talked about earlier are position. In one dimension we have x, so the corresponding operator is denoted by x cap, and the effect is, if it is operating on a state psi, it will just multiply the state by x. Pardon me? Yeah. Yes. No, here it is actually, as he said, this will be in a dual space. So if this is a ket, it will become a bra. So it is the star which is required on the O operating on side will give you another state, it is the complex conjugate of that state. Then you have another observable which is momentum. हाँ kappa है ना. Momentum P in quantum mechanics we represent it by this. So if you have operator P operating on psi, it is equivalent to minus IH cross d psi by dx. In 3 dimensions it will become minus IH cross gradient operator. Okay, and as Professor Kanere has said that all other quantities that we can think of, like kinetic energy, potential energy, total energy, angular momentum, they can be represented in terms of position and momentum. So we can derive the or write the operators for the remaining observables in terms of these two quantities. So these are the main two operators that we would like to work with. And we define what is known as the expectation value. Yeah. Any operator in the sense operator corresponding to some observable quantity. So kinetic energy, for example, that you can write in terms of P.
You need to apply this first, then you calculate operations.
Yeah, for example, if I have a potential, say my potential energy or potential operating on a particle or the force operating on a particle is such that it has this much potential energy, 1/2 kx square, harmonic oscillator. So it will be equivalent to saying that operator V operating on psi will be 1/2 k x square operating on psi. Yeah, so x operates on psi and then again it operates on psi. So x operating on psi may give you some phi and then x square operating on psi will be x operating on phi some other state. Similarly, if you have kinetic energy, it is p square upon 2m. So it will be this p operator operating twice on the state divided by 2m. That will give you the operation of p square. Okay. Then we define what are known as the expectation values. So expectation value of an operator. So if I want to find out x, average x, this will be psi star x operating on psi dx. And as Professor Kanere had written that day, this is equivalent to saying that you have x, rho x, where rho is mod psi square. But here, since x is only a multiplicative operator, it doesn't matter whether you write psi here or here. But in general, if this operator is like a momentum operator, which is a differential operator, then it will not be correct to write just p square. Therefore, we have to write in this particular fashion. So, expectation value of p will be psi star minus IH cross d by dx operating on psi dx. So, this is the expectation value of operator p in the state psi. So this is basically an average value as we define normally in. So therefore he had given this analogy that it is kind of a weighted average of that particular quantity. Rho is the probability distribution. So in our case rho is mod psi square, except that since you can have operators which are not just multiplicative, you have to write it in this particular fashion. So what is the meaning of expectation value? What is the physical significance of this? So suppose I have a state psi and I make a measurement of say momentum of that particle If it is an eigenstate of the momentum operator, I will get the corresponding eigenvalue. But if it is any general state, and I can write that general state as a linear combination of the momentum operator eigenfunctions, then I will get one of the eigenvalues, and that original state psi will convert to that particular eigenstate corresponding to this eigenvalue. Okay, we will come to this example later, but currently what I am trying to do is explain what we mean by expectation value. So if I make measurements, do I expect the expectation value to be the result? That is what I am trying to tell. So let me take an example, very simple example. Suppose you have a die, and because you throw dice and you can get any outcome 1, 2, 3, 4, 5, 6. If you try to calculate the mean of these values, what will you get? This is 3.5. But this is not any of the outcome. The outcomes are only 1, 2, 3, 4, 5, 6. So the mean value that you are getting is not a possible outcome of a measurement. So when I am talking about an expectation value here, it may not be a result of actual measurement. So what does it tell me? So what it tells is, suppose I have lot of similar states, say hundreds of states psi, identical, and I make a measurement of some quantity, say energy of this particle. Okay, so same measurement I am doing on the same similar states. Why I am taking different states? Because the moment I try to measure, I will convert that state, that state is going to collapse to one of the eigenstates of E. So if I make another measurement on that, I am not going to get any result, different result. So therefore I am saying that I am preparing many such states of same type, say 100 of them, and I make a measurement of energy of this, I can get different values. Although the state is same, this state is made up of a combination of eigenstates of E. So the probability of getting value E1 is different, probability of getting the value E2 is different, and so on. So if I take the measurement and I see what is the result of all these measurements and take a mean of that, that is what is meant by expectation value. So expectation value is not something which you expect as a result of a measurement. It is the mean of many measurements made on the same state and taken an average.
So it may not be the actual result.
Yeah.
0.5
So actually I think Sriram has made animation केलं त्यांनी. He has made a two-state system, and you make a measurement. So he has represented the state as a combination of two states, and then you make a measurement. So whatever is the corresponding. So if I write psi as some A into psi 1 plus B into psi 2, and psi 1, psi 2 are eigenfunctions of whatever operator for corresponding to which I am doing the measurement. Then when I make a measurement of this, I will either get psi 1, even psi 1, suppose energy. So these are suppose eigenstates of energy. So I have H operating on psi 1 giving me E1 psi 1, and H operating on psi 2 giving me E2 psi 2. Now if I make a measurement of energy on psi, I will get a result E1 with a probability mod A square, and I will get the result E2 with a probability mod B square. And since there are only two possible states, mod A square plus mod B square has to be 1, because you will get one of the results. So what he has shown there is you make a measurement and you try to count how many times you are getting psi 1, how many times you are getting psi 2, and then take an average of that. That will give you the expectation value. But it is not, it may not be a result of any actual measurement. That is the important point.
I just add one
Yeah.
point. So Amit has also agreed to demonstrate the IBM calculation tomorrow. And there again, Amit will show that you have to run the same simulation multiple
Yeah,
times,
yeah.
generate the curve of frequencies, which is called shorts. Histograms. So and that's the same point that he'll make again tomorrow.
the other way around. It is because of this interpreting that you have to run it so many times. So if somebody asks, I mean, those who do only computing, without understanding this, would just do it many times to get the answer.
But why they are doing
Why they have to do it so many times,
Yeah.
and how the error propagates,
One confusion
is
happens.
because of this.
And the more number of times you make the measurement, you will be coming closer to the actual expectation value. If you do only 2 or 3 measurements, you may be very far away from the actual expectation value.
ये confusion होता है स्टूडेंट को कि आउटकम क्या आएगा, 5-1 आएगा, 5-2 आएगा, आउटकम 5-1, 5-2 नहीं आएगा. As she said, outcome will be either even or even.
Yeah.
But sometimes students get confused कि outcome 5-1 होगा या 5-2 होगा. If I is A psi1 plus B psi1, student used to think the outcome is the measured value will be
But that also must know the limitations. Small problems that we normally run in the class. Running 500,000 times or whatever is easy. It's doable. If you have an involved problem, and if taking one average takes enormous time, taking a million averages won't be feasible. That is one of the limitations of that right? I mean, it's possible.
But one more point, I think Amit had the question, you have taken the example of psi equal to 2 state siding.
Yeah.
A psi or
Yeah,
psi.
yeah.
And I think
So,
at 3, 4, etc., the same holds.
Yeah.
Nothing changes. That was your question, right?
no, he was saying whether the result will be, so basically the measurement output will be even, and after that the state will be psi1.
Right, but if you had say 4 states, psi 1, psi 2, psi 3, psi 4, the same will hold.
Yeah.
A, B, C, D.
Yeah.
There's no, it's not, 2 is nothing special.
Yeah. So in general you can say if you have this, you can write this as a n psi n, n going from say 1 to infinity also. Then the and corresponding eigenvalues are say ens. Then after the measurement, if you get a value E1, it will be with a probability A1 square. Get a value E10, suppose, it will be with a probability A10 square. And the corresponding state after the measurement would be then psi 10. This original state will collapse into psi 10.
what would be observed, ma'am? Either E's be observed or I's be observed.
You are doing a measurement, so measurement is for energy. So measurement will give you a result of energy, but that state will go from psi to psi 10. If the energy that you get is E10, then this psi will go to psi 10 after the measurement. Is that clear? Any confusion? I don't see on the faces whether they have understood what we are discussing.
Still the state will be in superposition.
No. After the measurement, it will not remain a superposition. It will become one of the eigenstates of that operator of which you are making the measurement. Yeah, it will collapse into one of the eigenstates of that operator. Okay? Is it okay? Should I go ahead? Okay, another quantity which we talk about is the most probable value. So actually the most probable value is a quantity which is unobservable. When you actually make measurements, you get one of the eigenvalues. So which eigenvalue has higher weightage? That will be the most probable value. So this has an actual result, this can be an actual result of actual measurement, but this will not be a result of an actual measurement. That is the difference. And I just thought that hydrogen atom you must have done long back, some of you might remember, some of you might not remember, but the corresponding wave function, suppose I take the 1s state of the hydrogen atom, the wave function goes as e to the power minus r upon a0, where a0 is the Bohr radius apart from some constant, and if you write in 3 dimensions, you will have a factor of, so this A contains that 1 upon 4 pi. So if you try to plot the radial probability density, so I'll call this rho of R as a function of R, you see that it has something like this behavior. So what I say is this is the most probable value if I make a measurement of position of the electron which is circling around the nucleus, and this turns out to be A0. But if you try to calculate average R, that is expectation value of R in this state, which is the 1s state, you get a value 1.5 A naught. Okay? So there is a difference between the most probable value and the expectation value. Most probable value will be a result of some measurement. Expectation value will be just an average value. It may not be a possible result of a measurement. नाही सांगू शकत कारण एक सगळे इक्वल आहेत ना, सगळे इक्वली प्रोबेबल आहे. पण समजा आपण तुमचा डाय समजा वेटेड काहीतरी त्याला केलं आणि त्याच्यात आपण म्हटलं की एका पर्टिक्युलर ह्याची व्हॅल्यू जास्त आहे प्रोबॅबिलिटी, सो दॅट विल बी द मोस्ट प्रोबेबल व्हॅल्यू.
And then his question was, so what is now the commonly accepted model? So this is that. So what she has drawn is the solution of Schrodinger equation for one proton, one electron. Yes. And this is one solution, and there are other solutions which are the excited states.
So actually you, when you solve karta, you solve this H psi. Now this psi will be a function of R theta phi. And why we are taking R theta phi? Because it is spherically symmetric potential. कारण त्यांचं Coulomb potential है. So it is dependent only on R. So we can choose R theta phi spherical polar coordinates rather than x, y, z coordinates. So we write this, and again the potential depends only on R. So we can write this as some function of R and some function of theta and some function of phi. Okay, and it so happens that if the potential is spherically symmetric, this is fixed for any problem, and that is actually nothing but the, I don't know whether you come across this, these are called the spherical harmonics. Okay, so this is always the angular part of the solution, and the radial Schrodinger equation actually that we get. So you separate the 3-dimensional Schrodinger equation, you separate into R equation, theta equation and phi equation. You get the solutions for each of them separately, and the solutions that you get for this R, they depend on the principal quantum number n and the angular quantum number L. So they are actually NL dependence. So when I say psi 1 of s, it is n equal to 1, L equal to 0. So this is the 1s state, this is the lowest energy state, and the higher energy states can be psi 2s when n is equal to 2, L equal to. So this is the lowest energy state. Okay. So these were some of the things that I wanted to revise. And as I said here, that the most probable value is A0 and the expectation value is 1.5 A0. Depending on the symmetry of the problem, it may happen that these two are same. But most of the times when the potential is such that it is not symmetric or skewed, then they are going to be different.
What we measure, that is expectation.
No, what we measure, we are, when you do a measurement, you can get a value which can be the most probable value. Average value may not be a result of measurement. That's what I said, that you make a measurement, you get different values. Average of that is what is expectation value.
When we go for expectation, most probable sufficient.
Most probable value is not always the result that you are going to get. So we are going to discuss that. That's what we said, that if you generally write any function psi as some an psi, n where psi n's are the eigenstates corresponding to some observable En. When I make a measurement of this observable, I am going to get any of the E1, E2, E3, E4. Most probable may be the lowest value, E0 or E1, whatever it is. But it is not necessarily that that will be the always, because it's that's what we say, quantum mechanics is a probabilistic theory. Huh? No, with equal probabilities means all are not all are equal, but you can get any value with this probability. No, that's not the case. Whichever is higher is not always the case. You can get, whenever you perform different experiments, you can get different eigenvalues. So that's what is given in that simulation on your LMS. That you have a state and you are performing simulation. The probability of one state is say 0.7 and the probability of other state is 0.3. It is not that always you will get the one with probability 0.7. You can also get the one with probability 0.3. So it is not that the most probable, that is the probability associated with the one, that is what you will always get, because it is a random process. So therefore, getting the average is important.
You are not getting proper result. You are expecting higher probability.
No, we call it the most probable because the probability is higher, but it is not necessarily that the result will always be that. That is the important thing to understand.
Unexpected promotion of
Yeah.
output should be
In quantum mechanics, you don't expect.
That is the problem. That is a true problem.
Maybe the question is what is the purpose of
That's why you have to learn it so many times.
That's what I am saying, that expectation value tells you the average value.
Yes.
Yeah, that's all.
Okay. That is not threshold value.
No.
Like threshold will be
Nine.
that is average of all the outcomes of measurement.
All possible outcomes with whatever probabilities as defined by the state.
Again,
So no, we will also do an example. I am going to do an example where we will actually see this.
I think they are asking why do we need mean value?
So, like Amit is saying, I think the important point is, it is the expectation value, but let's not downplay it just because it's not an exact solution in the conventional way.
Yes.
It still has a lot of information. It has information that Shivsagar madam has drawn related to that probability distribution function, which is why when Amit demonstrates it tomorrow, the same simulation has to be done multiple times, which is your question. And this is a big paradigm shift from how we work in digital computing. You do one simulation, if you do the same again,
You are going to get the same result, but here that may not happen.
it will not happen, which means you have to do this many times. You reproduce basically that curve, and then you draw your conclusion on what is, in your view, the right answer. So it's a big change, and which is the entire reason you have to, like Professor Kanere said on the first day, quantum mechanics you just have to accept. There is no way to explain. And in that sense, the experience that we have of digital computing is going to be very different. So don't feel that expectation value is not useful. It is useful. And of course, that's all that you can get out of it.
So most probable value is one possible outcome of a measurement, but average value is more important because it tells you how the system is. Yeah.
Draw a histogram, you will get most probable.
Okay, so he that day he had already did the. Huh.
LMS nodes also the probability is given as mod psi square.
That is probability density. Mod psi square dx. This is the probability of finding a particle between points x and x plus dx. So this is probability. Mod psi square is the probability density.
Something which is tricky mathematics.
That's a typo and he corrected. So sorry about that. But like she said, when you integrate that, you get 1. Remember that, and then back out that since there is dx and psi square is probability density.
So although I am calling it density, it is 1 upon length. In one dimension, 1 upon length. In 3 dimension, it will be 1 upon volume. But since it is related to the dimension of the space that we are talking about 1D or 3D, we call it density, probability density. So mod psi square is probability density.
And in summation, whatever comes left to that was called operator. So summation A into size A, that was called operator. But in this case, we called mod A square as a probability.
Now, in general, if you have a variable x or something, you have some, normally if you say that rho x is the distribution, okay, and you want to calculate some quantity, average of some quantity, say A, this is an observable, okay. So this summed over all x, now since it's a continuous variable, you take an integration. If it's a discrete variable, you will take a summation. So this should give you the average value. That is what we are saying. So this will be, and now what we are saying in quantum mechanics, each observable is represented by a operator. So this will be the expectation value of the operator A, which corresponds to this observable A. But this observable, or the operator, as I have shown, that if you are talking about the position, it's just a multiplicative operator. So it doesn't matter if I write this as this, but if it's a momentum operator, then it will not be correct to write the momentum operator here and do this. So in quantum mechanics, what we say is we define this as psi star and then the operator operating on psi dx. This is the expectation value of operator O. Or if you say E, this is A, this will be operator A. Is that clear? Okay, so time dependence we have taken care of. So what we are saying is now if the potential is not time dependent, we will separate the time dependent part. We already know the solution, and whatever is the time independent part, this is your time independent Schrodinger equation, and this operator minus h cross square upon 2m d2 by dx square, this corresponds to the kinetic energy operator, this is the potential energy operator, and this is called the Hamiltonian, which is an operator for the total energy of the system. Okay, so this E is the corresponding energy, and these psi's then you can say are psi E, they are actually the eigenstates of corresponding to this observable energy. Okay, so this is what we actually solve when we solve for a particular problem. And then one few more things that I wanted to repeat was, we had talked about the properties of this psi first day, and later on I think Professor Kandere also again emphasized that psi has to be continuous. Since it's a second order differential equation, the first derivative should also be continuous. So psi has to be continuous, d psi by dx has to be continuous. It has to be single valued because mod psi square gives you the probability. So if psi is multi-valued function, then probabilities will be different at same position. So that is not correct. And the last thing is mod psi square dx has to be less than infinity. This is what we call as the function should be square integrable. That means in nowhere in your space it should become infinite. So it should remain finite throughout. And it is not identically equal to 0 everywhere because it has to represent a particle in the system. So mod psi, psi cannot be 0 everywhere in your region of interest. So these are the properties that psi has to satisfy. This is possible okay when Vx is a continuous function. Now suppose Vx has some discontinuities. Will psi still satisfy the same properties? Suppose I am talking about a potential which is like this. Here it is 0 and here it is V0. So there is a finite discontinuity in the potential. So still the wave function is continuous, the derivative is continuous, or then those conditions are not necessary or will not be satisfied. No, but what do you think? You have the equation here.
Second derivative will not
V changes. We are changing, then how it will affect the answer of this? You have to include the answer will be continuous.
V changes discontinuously. Still, do you have to worry about these boundary conditions? They are in effect, irrespective of V.
असं घ्या किंवा असं धरा तुमचा V असा आहे.
We can say, sir, when piecewise it will satisfy.
Yeah.
In this range it will satisfy. In this range.
So if you have a finite number of finite discontinuities, then also psi will satisfy all these conditions which we have talked about. Only if V has an infinite discontinuity, V is something like, suppose here the potential becomes infinite, then the first derivative will not be continuous. In all other cases, nahi hona. So only when you have an infinite potential at some point, d psi by dx will not be continuous. In all other cases, when you have finite number of finite discontinuities in V, still d psi by dx will be continuous. So it will satisfy all the properties that a wave function or solution of the Schrodinger equation should satisfy. Okay, so now I think I can start with the problem and then maybe we'll stop at 1 o'clock. Infinite potential well. So in general I was saying that this, for example, if this is some f of t as a function of t, the function is discontinuous, but the derivative is discontinuous. Okay, the derivative, this is a linear function, so derivative is some value here and then here it is negative. So the derivative will be discontinuous, but so whenever the discontinuity is finite, you still have, so if the potential is discontinuous but it has a finite discontinuity, still you can work with the second order Schrodinger equation. And second thing which I wanted to point out is time derivative. So since the time dependent Schrodinger equation is first order, you have dabba psi by dabba t, isn't it? Or phi, whatever was there. Some function of some c phi. So you had only first order derivative. So therefore time derivative is not so important in this case when we are solving the Schrodinger equation. Okay, so let's do a problem. One question which I wanted to put was, if we know the Hamiltonian at all times, hence we know the wave function at some instant of time, can we predict what will be the wave function at some later time or what was the wave function at some earlier time? So can we talk about the evolution of the wave function if we know the wave function at one particular time? This I am leaving it to you to think about. Okay, so we will do the problem of particle in a box. So you have a particle, single particle in a potential well from say of length L. The potential outside this well is infinity. So V of x is equal to 0 in the region 0 to L, and it is infinity otherwise. So in this region, what will be the Schrodinger equation? V of x is 0. So this term will not be there, is equal to E psi. So between 0 to L, this is the equation that we have to solve. So if I substitute this 2me upon h cross square as equal to k square, E is positive, all these quantities are positive. So energy is going to be higher than this. We will discuss that also sometime later. So basically I am trying to solve d2 psi by dx square plus k square psi equal to 0. So this is a very familiar equations to all of you. So what are the solutions? Either you can write them in terms of e to the power plus minus I kx, or in terms of sin kx and cos kx. So general solutions, so it's a second order differential equation, there are two linearly independent solutions. So any general solution I can write as a combination of these two. And then I have to put the first day I talked about boundary conditions, but currently I did not talk about that. Okay, so what we said was the four properties that a wave function has to satisfy. In addition to that, you have to use the boundary conditions. So here, what are the boundary conditions? The particle, since the potential is infinite here and here, the probability of finding the particle in this region or in this region is 0. It cannot penetrate this infinite high wall. Okay, so psi has to be 0 here and psi has to be 0 here. Okay, so what I get therefore at psi of 0, that is when I am writing a general solution, I should put a boundary condition that psi of 0 is 0. Because outside this the wave function is 0. So it has to be 0 here. Similarly here it has to be 0. So psi at L has to be 0. So if you put this, what will you get? Sin 0 will be 0. So you will only get b cos kx is 0. That is possible only if b is 0 everywhere. Because this will depend on x. So this gives me a into 0 plus b into cos kx is 1. When x is 0, this will be 1. So I get b to be equal to 0. Okay? So one boundary condition gives me this, and the other boundary condition therefore is a sin kl has to be 0. Because at the other boundary of the well also the wave function has to be 0. So that gives me this. So that tells me what are the values of kl. So what will be the values of kl, possible values? A is not 0, Why? If A is 0, then it will mean that everywhere the wave function is 0. So it is not a physically interesting situation, the wave function is 0 everywhere. So therefore this is 2n pi? Only n pi, na? Huh? For any value of n. Okay. Again we will not take n to be 0 because it would mean it is 0 everywhere. So we will say n going from, in general this is true, but here any integral, non-zero integral value. Okay, so this boundary condition here puts a restriction on k, and k is related to the energy. So this boundary condition actually quantizes the energies, allowed energies. Okay. So what will you get therefore? E will be, E is h cross square k square upon 2m, and from here you will get k to be n pi upon L. Positive and negative are same, so we will forget about negative values. So it will be h cross square upon 2m, and k is n pi upon L. So these are the possible eigenvalues. I will label them as En. So first thing is you get discrete energy values. All energies are not possible. Only certain energies are allowed. So quantization of energy is the first condition. The lowest value will be with n equal to 1. So that is not 0. So you will always have a 0 point energy. The lowest value is not 0. And that I had discussed on the first day that if you say energy is equal to 0, that would correspond to kinetic energy 0, potential energy 0, that means the particle is not moving, so it will go against the uncertainty principle. Okay? So that is not allowed. So every quantum particle has to have a 0 point energy. 0 point energy. And that is also called the ground state of the ground state. And also higher n values, whatever you get are the, so suppose this is the first pi square h cross square upon 2m, this is the ground state, then you will have 4 pi square h cross square upon 2m, this is called the first excited state, then you will have somewhere here 9 pi square h cross square upon 2m L square. This is the second excited state and so on. And corresponding wave function, if you try to draw, this is a sine function. First when n is equal to 1, so your solutions are now what? Psi x is equal to a sine n pi x upon L. So when n is equal to 1, it is just sine pi x upon L. So wave function is this. The next one will be something like this. Third one will be like this and so on. Yeah. And second thing is also there that energy goes as inversely with L. So the smaller the box is, that means you are trying to confine the particle, then the energy is higher. If your box is broader, the 0 point energy will be lower. Yeah, that will also be less, and the lowest energy will also be less if L is larger. So the more you try to confine the particle and all its energy, see here the potential energy is 0. So the total energy that you have here is the kinetic energy. So more you want to confine, the higher the kinetic energy becomes. Momentum increases. Any questions on this? Okay, if I take this this solution or maybe any one of these solutions, if I don't put these boundary conditions, what are the solutions going to be? They are going to be periodic functions throughout the space. The moment I put the boundary condition, I am just getting this much of this sin x. So the boundary conditions actually restrict your propagating wave to this kind of wave. So तुम्हाला काही कमेंट करायची याच्यावर?
These are the standard standing waves if you look from any point of view. So you have generated classical quantum equivalent of standing waves.
But generally, if we had not put the boundary condition, any possible value of energy was possible for this state. Okay, this represents a free particle. Huh? हल्ली जे म्हणजे ऍक्च्युली 90 साली जेव्हा नवीन क्वांटम डॉट्स वगैरे असं नॅनो टेक्नॉलॉजी सुरू झाली तेव्हा पहिल्यांदा जेव्हा असं झालं की तुम्ही छोटा केला तो पार्टिकल तर त्याच्या म्हणजे ऍब्सॉर्प्शन स्पेक्ट्रामध्ये ब्लू शिफ्ट दिसते असं लोकांनी म्हटलं. सो दॅट वॉज एक्सप्लेन बेस्ड ऑन दिस क्रूड मॉडेल. Basically, if you have suppose you have a semiconductor material with some energy gap, and you have another semiconductor material outside this with a larger energy gap. Semiconductors are used what would you do? Normally you have electrons in the valence band, and when you shine light or whatever, you give some energy, it goes to the higher state. So if in this region you have, suppose this is the valence band and this is the conduction band, and in this region, let's say that their valence band are aligned, but energy gap for this is different. So the conduction band is higher. Then whatever electrons are in this region, they are not allowed to go to that region because they don't have enough energy to go to that region. Because they cannot overcome this energy barrier, which is the band gap. So this is a kind of well, not an infinite well, this will be a finite well. So depending on the difference in their band gaps, you can decide what will be the height of the well. क्वांटम डॉटच म्हटलं ह्याला ऍक्च्युली काय म्हणतो आपण कोअर शेल पार्टिकल. नुसता एक क्वांटम डॉट असतो तेव्हा एक असतं आणि हे कोअर शेल म्हणजे कोअर मटेरियल इज डिफरंट, शेल मटेरियल इज डिफरंट. या येस, changing the size, changing the material. Basically, this gives you a way, because in atomic structure, like if you are talking about an hydrogen atom, the energy levels of the hydrogen atom are decided by nature. You can't change them, or for that matter, for any atom, you can't change them. But if you can make quantum dots or these semiconductor nanoparticles, then by changing the material of the nanoparticle, by changing the shape of the nanoparticle, by changing the size of the nanoparticle, you can change the energy levels. So that was the basic thing, important thing for nanoscience, and that is being used in nanotechnology. Okay. So I just also wanted to do one or two things more. That I had taken a well which was not symmetric, say from 0 to L. Instead of that, if I take a well so it is same. This is from 0 to L, this is from minus L by 2 to plus L by 2. I can solve the equation. So the boundary conditions that I put here were at psi 0 and psi L. Here I will have to put at psi L by 2 and psi minus L by 2. Do you expect similar solutions or different solutions? इथे पण V0 आहे. इथे V0 आहे. So म्हणजे इथे ह्याच्याऐवजी now I am saying it is from minus L by 2 to plus L by 2, and otherwise it is infinity. I have just, so what I have done here? Do I problem again, or it is the similar problem and I do some transformation and yeah. So basically what you have done, you have shifted, you can say the x along the x-axis, you have gone from 0 to minus L by 2, and so this L comes to L by 2. So if in my solutions here, I say x prime is x minus L by 2, I should be able to get the result. I don't have to solve the problem again. Like, intuitively, physically there are similar problems. So I don't have to solve, I can just go from here to here. And why I have gone from here to here is to just show that this is symmetric potential. At about x equal to 0, if I replace my x by minus x, it is an even function. Okay, so when your potential is an even function of space, then the solutions that you get, they are supposed to have, or they are said to have definite parity. That means they will be either even or odd. So here you have seen that I have rubbed that now, but the initial function that I had drawn was even. The second was 1, 7, and what I had drawn first was this, second was this, third was this. So this was even. If I take the center of the well, so therefore I have shifted actually to show that my center of the well here was L by 2, instead of that now I am having at 0. So the first wave function will be even, the second will be odd, the third will be even, and so on. So the wave functions have definite parity, we say. They are either odd or even when your potential is symmetric. And therefore, what do you expect the expectation value of R here, or X, where the particle is most likely to be found, and what is the expectation value of X? So in the ground state, your wave function has maximum here, corresponding mod square if you do, also you will get a maximum here at the center. So most probable value of X will be what? The center. Okay, here it will be L by 2, here it will be 0. And if you try to calculate the expectation value of X, what will you get? In this case it will be same because it has a symmetry, inbuilt symmetry. So in this case again it will be your expectation value of X if you try to calculate mathematically. So that is the difference. If you have some symmetry in the potential, you can expect the two to be same, but otherwise they will be different, as we have seen for the hydrogen atom case. Should we stop or should? Okay, so we will stop, and I want to continue from this. One example I want to do where we have a general function, and we will. So what I just want to say here is, so I will label my wave functions now by psi n. So what is the solution that we got was our energies are Ens, which are n square pi square h plus square upon 2m l square, n takes all integral values, and the corresponding wave functions I label as psi n. They are sine n pi x upon l, and there was a constant a which you normalize, it will turn out to be 2 upon l, under root 2 upon l. So these are the corresponding wave functions. Now as Jog sir was saying that your Hamiltonian is a Hermitian operator. So first thing is what we have seen is all these eigenvalues are real. The corresponding wave functions that you have, they can be normalized and they are linearly independent and orthogonal. So if you try to calculate integral psi m star psi n dx from 0 to L, this will be 0 if m is not equal to n. Okay, and since I have normalized this, integral psi n star psi n, this will be 1. Okay, so I can write this together as delta mn, Kronecker delta. If m is equal to n, it will be 1. If m is not equal to n, it will be 0. So these wave functions, they form a basis They form a complete set. So they form a basis for this problem. So if I have any general function which is representing my particle in this well, I can write it as a linear combination of these scions. So these scions will form a basis for this vector space or Hilbert space for this problem. Okay, so we'll stop here, and from this point onwards we will continue.
Come back 15 minutes early.
Sorry?
We come back 15 minutes early.
Yes, yes.
So 45 instead of.
Yes, so it's exactly one.
So we'll go by car or something.
The bus is there.
Better to do that. Otherwise, we extend it a bit more.
Yes. Okay. So we'll be back by 1:45. We will start at
Okay, so I thought that I will take an example based on this problem. So we have solved for the particle in an infinite well. These are the eigenfunctions and eigenvalues. Now I take a general state. So let me say that I have a function, say f of x or psi, maybe call it at psi, at some time x t equal to 0, which is ax for I am taking a general function and I want to show how we can expand it in terms of eigenstates of this and how we can talk about the probabilities then. So this is any general state. This is in this potential well, any particle which is represented by this function. So if I want to draw this, okay, so this is the function psi x0 at some time t equal to 0. Now I use the fact that these psi's, they form a basis for this space. So I can write this psi of x0 as a linear combination of these psi's. And as we had done earlier, and also Professor Zog has shown, that therefore I can calculate this psi n as so Cn will be the product of inner product of psi n with psi. Okay, so I will not do the mathematics, I will just write down what I get. So this Cn turns out to be 0 if n is even, and this is equal to 4 root 6 upon n pi square minus 1 to the power n minus 1 upon 2 if n is odd. So is that clear? I am taking a general state, a particle in this potential well, which is not an eigenstate of this problem, and I am using the fact that these psi's, which are the eigenstates of energy, they form a basis. So I can expand this general state psi as a linear combination of this. And here I know psi's, what is unknown is these Cn's, the coefficients, which I can find out from this scalar product. So basically it tells me that if n is even, those states will not contribute, only when n is odd those states will contribute. And now if I make a measurement of energy on this state, then the probability of getting the value En will be what? En's are known. Okay, this is a general state, so it is not an eigenstate of the energy, but I am making a measurement of energy. So possible outcome will be any of these states with some probability. So what is that probability? Mod of Cn square. So to get a value E1, the probability will be C1 square. To get a value E2, the probability will be C2 square, and so on. Okay. So if you calculate, what we will get, the values that we get is, so if I say P1 is the probability for getting a value E1, that is equal to C1 mod C1 square, and this turns out to be 0.9855. P2, which is mod C2 square, it turns out to be 0.2464 and so on. So the values are going to decrease. And the other thing that you can see is if we normalize this state, then mod C1 square summed over all n's should give me 1. Currently this is not normalized the way I have given, but you can find out A such that this is normalized, and then in that case if you try to calculate this sum, this will be equal to 1, because the total probability of finding the particle in one of the eigenstates has to be 1. Now why we are getting P1 to be very large is, see at this function, this is not exactly similar to what was the eigenfunction, but if what was the eigenfunction, it was something like this. So it was peaked in the center, the values at the ends were 0. So in some way this function has some similarity with the lowest eigenvalue, therefore the probability of getting the value even is maximum, but it need not be always the case, it will depend. So I am giving you a problem that you can solve later on. No, I have a part, like I start with a state in which, so we will write down what is the function and you will do the expansion. So I am saying that initially my particle is in the left half of the box, it is not going to be in the right half. So it is going to be in the left half, and it can be in the left half with equal probability. So what can be its wave function? So instead of this psi which I have taken now, I am taking a different psi. So tell me what should be this function. So this is going to be different. So what should be the function from L by 2 to L? 0, because I am saying that there is the probability of finding the particle in the right half is 0. So the wave function has to be 0. And the probability of finding the particle in the left half is same everywhere. That means it can be anywhere from here to here. That means, what does that mean?
Constant.
So it has to be a constant. Okay. So sum A. So take this and find out. So you will get different values for P1, P2, P3. So it will depend on the starting state. That is what I wanted to emphasize, that if the starting state happens to be closer to one of the eigenfunctions, then corresponding probability will turn out to be largest. That we will call say most probable. But again, I am emphasizing that although I am saying most probable, it is not that when you perform an experiment or when you try to measure the energy, you are going to get that value. All values are probable, but with certain probabilities. And therefore, it is important to do the or repeat the measurement again and again. Huh?
Fraction of times, if I repeat the measurement 8 times,
Yeah.
and if I get say, no time.
stationary state. The modular square is independent of time. So mod psi square is independent of time.
Is it working? So when mod psi square is independent of time, we call them as stationary states. So stationary states are the ones for which the probability does not depend on time. The wave function still depends on time. Okay, what else is remaining? Then I wanted to discuss slight modification of this. So instead of an infinite potential well, now suppose we have a finite potential well. Currently, since it was an infinite potential well, the probability of particle being outside the well was 0. Now instead of that, if I have a well so this is finite. Now few questions I will ask and then we will discuss actual problem. This is the given potential. So I am drawing different values of for energy. Which of these energies are allowed, can be allowed energies? Can I have total energy to be this? Negative. So normally I find there is a misconception. People say that if the energy is negative, it is a bound state. But here the way I have drawn, what is the minimum of the potential? 0. And otherwise the potential is some positive, is having some positive value. If I say that the energy is E1, what will be the kinetic energy? Negative. Can you have a kinetic energy negative everywhere? No. What does that mean? Is it a real situation, kinetic energy negative everywhere in space? So that is not correct. So this energy is not allowed. You cannot have a particle in this which has energy less than the minimum of the potential. That is important. So since I have taken minimum of the potential to be at 0, I am saying that negative energy is not allowed. In general, if I had written that this is some V equal to minus V0 and this is equal to 0, that means I would have shifted my scale of energy. I am saying this is my 0 and this is negative. Then you will have a negative energy value which will be a bound state. So basically the idea is your energy should be above the minimum of the potential, whatever may be. Suppose I have general any arbitrary potential. This is V minimum and somewhere some V maximum. Here also there is some other value. Then I should always have total energy which is greater than the minimum of the potential energy. Then you will have in this region the kinetic energy is positive, in this region the kinetic energy is negative. That is okay. Classically that is not allowed. Classically kinetic energy cannot be negative. So in classical physics you will say that the particle can only be here. It cannot be here or here. But quantum mechanically we do see that particle can be in a negative kinetic energy region, but everywhere kinetic energy cannot be negative. So this if you consider E2, go back to my original thing V0 is equal to V0. So I have an energy which is between V0 and 0. Is this an allowed energy state? Can this be an allowed energy state? Yes. Yes. Or no? Or no? As I said, kinetic energy here is positive. Kinetic energy here and here is negative. This should be allowed. Okay. So this will give me a bound state. And if I say that my energy is E3, that means particle is in the state E3, then everywhere the kinetic energy is positive, then it will not be a bound state, it will be a scattering state. Particle can move anywhere in space because of this. Okay. So we are interested in this energy E, just between these two. So I am not going to solve this completely, but I'll just indicate, and then we will just try to write down the nature of the wave function. So what we are going to do is we are going to solve this time independent Schrodinger equation. Let me say this is region 1, this is region 2 from minus L by 2 to plus L by 2, and this is region 3. So in the region 1 potential energy is 0. So the solutions here will be similar to what we have already done. Isn't it? So side 2 if I want to write, again I'll use that thing, 2 upon x cross square is equal to k square. So my side 2 will be some a sin kx plus b cos kx, as we had done in the earlier problem. And equation in region 1 and 3 will be minus x cross square upon 2m d2 psi by dx square plus v0 psi x is equal to e psi x. So this I can write as d2 psi by dx square So now it will become clear why I was discussing about the energy. We will have a bound state when energy is greater than 0 but less than V0. If your energy is greater than V0, it will be a scattering state. So we are only interested in the bound state. That means my energy magnitude wise is less than V0. So whatever I have written here, this will be a negative quantity. Or I can write this as minus V0 minus E. And I define 2m upon h cross square V0 minus E as some k1 square. Again this is a very familiar equation to you. d2 psi by dx square minus k1 square psi equal to 0 in region 1 and 3. That means for x less than equal to L pi by 2 and x greater than equal to L pi by 2. What are the solutions? In the first case when we had only this plus k square, they were oscillatory solutions, sine and cos, or e to the power I case. Now this will be decaying type, e to the power. Solutions will be e to the power. Maybe I'll write here. In general, I'll have say C, or let me call it psi 1, C e to the power minus k1x plus d e to the power, plus k1x. And in region 3, I'll have say f e to the power a1x plus g e to the power 2x. So these are general solutions of differential equation as we know. Now we have to put the boundary conditions. Now our basic thing is our wave function. We are saying we are talking about a bound state. So our wave function should be bounded. That means it should go to 0 when x goes to plus infinity or minus infinity. Because we have said that if it extends up to infinity, then your integral mod psi square dx would diverge. Okay, so the wave function has to go to 0 at plus or minus infinity. Now look at this. This is region 1. That means x less than minus L by 2. That is negative values of x. So what will happen for negative values of x if you put here? Because x is negative, so this will become e to the power plus something. So this will diverge when x becomes large. So this is not allowed. So this will happen. We can make c to be 0. So in region 1, you have the solution as just d e to the power plus kx. Is that clear to all? And opposite here. This is the region 3 is x greater than L by 2. That means x is always positive. So in that case this will diverge. So we have to put g to be 0. So this is the solution in region 1. This is the solution in region 3. And also because it is symmetric, you can actually show that, but you can also, because of symmetry, d has to be equal to f. X equal to 0 is from this. So what we have to do is we have put the boundary conditions for infinity. Now we have to match. That we are not going to do, but basically to find out the full solution, what you have to do is you have to match psi 1 and psi 2. Psi 1 at x equal to minus L by 2 should be equal to psi 2 at x equal to minus L by 2. Psi 2 at x equal to plus L by 2 should be equal to psi 3 at x equal to plus L by 2. So this is the continuity of the wave function, and similarly you will have to see the continuity of the derivatives, because we have seen that if you have a finite discontinuity in the potential, the derivative is still continuous. So similarly you have to say d psi 1 at by dx at x equal to minus L by 2 is equal to d psi 2 by dx at x equal to minus L by 2, and d psi 2 at dx at x equal to plus L by 2 is equal to d psi 3 by dx at x equal to plus L by 2. So by doing this you can actually find out the allowed values of energy, and you get the information about the wave function. You can normalize it. That I am not going to do, but you can see we can draw the wave function. So if you look at the lowest energy eigenvalue, if you remember what was that for a infinite potential well, it was like a sine wave, and which was going to 0 at the boundaries. Now what you are seeing is it's a decaying type of wave function in both the regions, because here x is negative. So this is also a decaying type of wave function. This is also a decaying type of wave function. So what happens? This function will extend So although in this region the energy is somewhere here, kinetic energy is negative in this region. Classically these regions are not allowed, but quantum mechanically there is a finite probability of finding the particle in these two regions. This is called tunneling. The particles are tunneling in this region or in this region. And this will happen for all. This is the ground state. Similar things can happen for the excited states also. So if you look for example the first excited state, it was something like that. So it will become like this. Again, since potential is symmetric, these are going to be either even functions or odd functions. Meaning? I don't think extract, because extract means you will have to. It is not moving because it's a decaying type of solution. No, I don't think it has a positive kinetic energy, because from this it is definitely having a negative kinetic energy. Yeah, I am understanding what you are saying, but I am not able to answer the question. I don't think that it is actually like as you see in this region it is moving, you don't see that way. But there has to be something which will.
This is a standing wave still, some modification of not a scattering mix.
Yeah.
So let's consider. We explain this is if you sure. But you want to extract from understand. Let's take a barrier actually. Just both sides. No, just both sides. So you're not shooting a particle from one side. What I'm saying is that take a barrier, shoot a particle from one side.
No, in that case it is actually a travelling wave. Then it's actually a travelling wave.
Extract a particle on the other side, and will also extract a particle which is reflected.
Yeah.
What happens inside? You go and sit inside, you will figure out. But you want to see what happens outside, have an experiment. This.
No, so what I can say is, if you had something like this, then there is a final. Then here you will see a particle. Here the particle will be moving. In this region, I don't know.
Then particle is
Yeah. Yeah. Yes.
Side. Right now outside the way.
At that time, in that situation, if the particle is moving, then it is.
I don't know whether we can say it is moving. I don't know whether we can say it is moving. No, here barrier is not infinite. Infinite barrier there is no probability. Infinite barrier it cannot penetrate. Finite barrier it can. So what we can only say is there is a possibility of finding the particle here, but there the particle is actually moving or not. That I am going to talk about that. Yes.
But it comes out as a kinetic energy. But that example means you have closed the barrier. I must take one and the other
Yes.
This side continues all the way up to infinity. The first case.
त्याच्यात असं आहे तुमचा हा इथे तुमचं न्यूक्लियसचं सेंटर आहे. न्यूक्लियसचं सेंटर आहे आणि इथून तुम्ही ऍक्च्युली बाहेर जाता असं होतं त्या केस म्हणजे जे बोलतात.
बाहेर झिरो पोटेन्शियल आहे. बाहेर इन्फिनिट पोटेन्शियल.
extending the infinity, then there is no tunneling.
In the conventional sense, if you mean
going to get that particle out.
in this case particle does not come out because
This is continuing, so it will die out somewhere.
but don't what is the meaning?
That's what I said, that if you have this, then you won't have a particle here. Somewhere here itself it will die. If you have a barrier like this, then you will see a particle on this side.
You want to see the particle,
I understand.
you have to put a detector inside. Let's take a case where you have a detector inside.
आउटसाइड म्हणजे ते इथे म्हणताय तुम्ही, इथे या रिजन मध्ये, या रिजन मध्ये जर तुम्ही ठेवला तर देयर इज अ फायनाइट प्रोबॅबिलिटी दॅट यू विल डिटेक्ट अ पार्टिकल. You will detect a particle. That's what. It has gone there, and like as we say, it's a probability.
Everywhere. Finding around everywhere. So think about the unseen particle in this sense. But if you are thinking about dancing particle in this sense, then the particle is dancing both ways. That's why it's a standing wave in infinite case. Plus K minus. It's an standing wave. Sine
Okay, so I'll take another. As it was being discussed, let's see about a barrier like this. Here the potential is 0, and all the way here you have a potential V equal to V0, and then you have some particles coming from this side on this barrier. Then again here, like classically, if you have a particle with some energy which is this, that means the energy is less than to energy required to overcome this barrier, the particle will not go to this region. So particle will be reflected. A classical particle will be reflected if it has an energy less than V0. But if you are talking about a quantum particle, you have incident particles here. There is a finite probability that they will go here in this region. But again, when they go in this region, here they are plane wave like solutions. Here they will be decaying type of solutions. So there is a finite probability of finding the particle here, but it will not go up to infinite. So it is not traveling in that sense. That is the idea. Okay. So what we do is we say that some of it is reflected, some of it is transmitted, and we talk about R and T. R is the reflection coefficient, which is suppose initial wave function is this, and whatever is reflected that I denote as psi r, and whatever is transmitted that I write this. This is equal to mod psi r square upon mod psi in square, and T will be mod psi t square upon mod psi in square. Yes.
Like in classical physics,
Yeah.
you will not have a container. That particle will not jump.
Yeah.
Quantum, how they move to the other side?
So that's what we are saying, that there is a finite probability that they can be found in this region. I am not saying they are moving.
The current is 0 in the worst
Yeah.
case. In this case, there is no current. Compute the current, and the reason is obvious. It's mathematical. That if you take a sine wave, then it is equal to plus and minus. Both cases are involved, so both components.
So J basically what I have defined as the current density that you calculate, that will be 0.
There is an electron, you takes both.
Basically, if your psi is a complex function, you get non-zero J. If your psi is a real function, you get a 0 J. So here what we have seen is the ray function is like this. It is a real function. So here j becomes 0. So total r plus t should be equal to 1. But t is not 0. That is what is important. But eventually what will happen? The wave function will die out. And in limiting case, if energy is quite small as compared to V0, then t would go to 0 and r will tend to 1. And the other possibility is a barrier. That means you have a very thin barrier and you have particles incident, and in that case it is possible that the particle will tunnel through this barrier and there will be again traveling waves on this side.
Let's continue this either way by quarter to 3.
Yeah.
We'll continue similar discussion. I have a free agenda. So you can sit here or I can.
So I was just going to tell the examples of tunneling. So that maybe you can discuss. I was having one is nuclear fusion in sun.
Yeah, you can that also go ahead and tell what is the tunneling.
So in sun's atmosphere, you know that hydrogen. So basically your protons, hydrogen ion.
He asked a question, I think why it happens. Somebody was asking why tunneling happens. Now what do you think why tunneling happens? This is the dramatic difference between classical and quantum. So the naive answer would be the reason is that it's a wave phenomenon. But that's a naive answer. And
So you would like to take this?
why tunneling happens.
Tunnelism.
Mechanical behavior of a particle. And that's the conceptual difference. So you have any why? Mathematically it's very clear.
So in the first lecture I said that a language, if I try to describe a language which says that this is a wave and particle at the same time, right, you will have certain difficulties. So it's better to have a mathematical language. A clear physical understanding, I will say, look at that. The decay in solution is obvious because the exponential k square, that becomes changes the sign, which is the kinetic energy part. So what parameter are left with me? My potential is fixed. Only one parameter, energy. I can vary energy and solve the differential equation again and again. That's what we said that we have an eigenvalue problem. So I change the energy in this case and in this case, same energy. The moment you change the energy, this will start moving up and down. This will change. And for a particular energy, you will find that the wave function and its derivative becomes continuous. This has to be exponential. My drawing is bad. So this becomes like exponential going. There is only one energy that will happen. When you start going from this to that, right? I can go up again and I will find another energy with the third energy, and so on and so forth. Not infinite in this case. This will have only finite number. I will make that comment. So how far it will go? Well, that physics tells us that if you have lower and lower and lower and lower, my wave function extends outside. If this is not infinite, then my wave, the differential equation will have a non-zero solution outside which is decaying. That's the reason that I will always find a particle, or I will have a probability of finding the particle outside the region. We'll leave this discussion, perhaps next few days we'll make it clear what happens. But there is no current in this particular, it's a bound state. In this particular case, the wave function is real, and it can be shown that in this case there is no particle current. In the earlier case that she discussed, there are two cases. That's the nucleus you are talking about. Something is inside, there is a barrier and something goes out. There is a particle current. In this particular case, barrier, a particle comes here and comes out, there is a particle current. In this bound state case, there is no current. So the question of particle going out does not come. It comes only if you have this case, not otherwise. So zero current situation. But that the tunneling, you can see that the tunneling, then this is clearly seen. Can you now make a comment where you, two examples that you wanted to give?
One was in the sun's atmosphere, you have protons, basically. So protons fuse to make helium. And that reaction, so they fuse and that reaction energy is given out, will give the power to the sun. Actually, these are two protons. So they are, like there is a electrostatic repulsion between them. So that is actually a pulsive potential that they have to overcome. So if they can overcome that means they can tunnel through that barrier, then they can fuse and the actual reaction can happen, otherwise not. So this is an example where they overcome the barrier and fuse together.
Come together.
From two H atoms fused with one HCl. That was one example. And the other example, alpha decay was the
Alpha decay is another one. This is a well-known one. The nuclear alpha decay happens, and it happens because of tunneling, because the barrier is still very high. If you classically calculate the kinetic energies that the outgoing particles have. And similarly here, the protons do not have enough kinetic energy to cross the Coulomb barrier, because Coulomb barrier is a bit too much. It's 1/r. And R,
normally happen in radioactive.
yes. So these are the two, and there are other, I'm sure there are other examples.
Why is I was thinking that in scanning tunneling microscope is very
Oh yeah, sure. Tunneling, it's tunneling microscope.
actively see the images of atoms. So earlier it was not possible to see the atoms in a solid. So now you can bring the tip of the scanning tunneling microscope very near the surface of the material. From there you can image the. And the other possible thing was this flash memory where the solid state this that we have.
This is tunneling.
Oxide barrier. So the electrons have to travel through that oxide barrier and then you can read and write. That is, these were actual examples of tunneling in device.
Means the real electron comes out of the barrier. Photoelectric effect is not tunneling. It actually overcomes the barrier. Yes. Tunneling tunneling. Absolutely. That's another very correct example coming from engineering. We really talk about diodes in the class, so except to tell what diode means, and then forget about it. We don't even know how to make diodes. Okay. So I will continue the discussion. I want you to ask questions, and we will answer a few things. But I will make few comments. Why learn quantum mechanics? The general intellectual answer is it's fun. The second answer is it gives you a reasonable background to understand parts of quantum computing. You will find that what we discussed in terms of wave functions, the actual wave functions and what you actually do are very detached. You don't talk about these wave functions there at all. But as he has pointed out, there is a deep connection. So that connection takes some time to establish. And my last answer, why learn quantum mechanics, is the same question that students, engineering, my own, not student, my own son asked me, or people ask, at 12th standard or a BSc standard, why should we learn quantum mechanics? This is the BSc students often ask. What is its use in real life? So that has no answer. No? Why should we learn calculus? This is the question that everyone asks at 12th standard. Now you know the answer and I know the answer. At least to have some background, it will work. Besides, this is what everyone is talking about. It's fun really to figure out that things happen in this way. It's an entirely different language. A few things that she has pointed out, I will repeat and then we'll go for your questions. We never had a concept of 0-point energy. The lowest energy that a classical state goes is zero, absolute zero. But you can't have a quantum particle having a zero energy. There is always some 0-point energy. That means the lowest energy in a quantum state is that must have some repercussions when you build devices, because they will always have some energy. You never get a 0-point state. The last point, another point that I will make is we didn't talk about this, but let me draw a picture and so pictures are interesting, but they also are somewhat loose. So one should take it with a pinch of salt. A mathematically rigorous understanding is always welcome, but I thought pictures understanding also helps. Then one can always make them rigorous. So I am going to draw a wave. For a particle moving in a plane wave, what is called a plane wave? A particle in free potential, quantum particle, zero potential, moving say in one, doesn't matter which direction. I am not going to draw a wave packet. I am going to draw. So this has a definite momentum, K or P. That's considered to be either a sine or a cos wave. Perfect sine, don't worry what I have drawn. Perfect sine or cos wave, whose wavelength is given by whatever that formula, French formula, the Brouille or whatever, by जास्त येतोय का? हे येतोय का? माझा आवाज मोठा आहे. ऑनलाइन चालू आहे ना तर No, I cannot. I agree. That's what I said. I'm not drawing a.
Machine is in some hall. The moment it is supposed to have produced, it is in a hall. That particle is in a hall. So it is finite one.
Yeah, sure. Sure. No. I mean, I'm just saying that if you shoot a particle, particle has to be everywhere. That's the point. But if you really shoot a particle with a gun, then it is not this. It is a wave packet. Correct. So that's why I didn't take a wave packet, because the next question is, he has already anticipated, it is in the hall, so it is not this. So if it is in the hall everywhere, right, it has a definite momentum, and I ask a question, where is it? I'm saying ideally I am having a particle in a definite momentum, so I draw it in wave. If I draw a plane wave, it is this. And now you ask a question that it has a definite momentum, and what is the probability of finding the particle anywhere in space, then it is mod square of that. Actually it is sine plus cos, and that's 1 everywhere, unnormalized, normalize it in some way you like. So try to understand. I have drawn only one part, cos plus I sine. I can't draw both. the propagation wave function is which everyone uses for a plane wave, normalization, whatever, we leave that. Yeah. So now it cannot be normalized. We can normalize it in the other way. So let's not go into that. But the point is that this has a definite momentum. That particular plane wave has a different. I plotted only one part. If you ask a question, so the point is I have measured or I know its momentum. Question is, do I know where it is? Now, if you ask the question where it is, you will take mod of this, square mod of this is my mod psi square, and that's 1 everywhere, or that's a constant everywhere if you take a finite volume. And that means I just don't know where it is. So if I make a measurement on that, somehow I missed where the particle is. The point was made in his discussion on the slit measurement. We try to figure out where the particle is and what is its momentum. You can get one at a time. If you want to get both simultaneously, you are in trouble. It's inherent. It's one of the whatever beauties or dramatic effect of quantum mechanics is simultaneous measurement. I can draw a wave packet if you like. Same thing. This wave packet cannot be described by definite momentum like this. This wave packet can be described by a Fourier analysis. Right, I can make a Fourier analysis and we will find various momentum components. Just take a Fourier transform. Like your electrical engineers do it every day. So I have multitude of K values or P values, and so if you ask a question, what is the momentum for this, I have no answer. I have an answer, but I answer with a error, if you like that word. If I ask a question, where is the particle? Well, the probability of that is small. I don't pinpoint that it is here. Just as I don't pinpoint where, what is the momentum? Now let me do this. Let me draw that. Now those of you, all of you probably understand the Fourier transforms. So moment I shrink this in one space, in another space, I get expanded version. Is that right? Is that you understand standard Fourier transforms? This must be true in T, omega psi. Yeah, you use F and so same thing. That if you sharpen it, your F will spread. That's what happens here. That's what I am trying to illustrate. And that means a simultaneous measurement of X and P. If you do simultaneously, that's what quantum mechanics is different. Then there is an error delta X in measurement, there is error delta P in P measurement, in your case similar, should be what? Of the order of by 2 H cross. Right? So you decide what you want. You want X. If I measure X only and not measure P, no problem. Let's get that concept clear. That if I measure one at a time, you can measure it as accurately as possible with the usual limitations of the apparatus. If I measure P, yes. If I measure both simultaneously, which is possible in classical physics because X and P is that's not possible here. That's not possible or can be proved rigorously, but those who are mathematical minded, then that is because xp minus px operators, which are called commutator, is not equal to 0. It can be rigorously shown that for two major operators, x and p, any two operators, if they're this, that is the commutator bracket, but that's xp minus px, both operators are non-zero, then simultaneous measurement, and this delta x and delta b is exactly how you define it in the statistical sense. Average j square minus j. standard deviation. What you do in probability theory, standard deviation. So that's something which is Heisenberg's uncertainty relation simplified and given in terms of language. One doesn't justify it, it's true. But if there are two operators whose measurement, whose commutator bracket is 0, you can measure them. Absolutely no problems. You can measure them simultaneously. They are not correlated in this sense. Yeah, sure. Yeah, sure. This is free today till 3:30 or whatever.
So see, if A and B are two physical quantities, that is operators observables, and you are given that they have common eigenbasis. I mean, the same set of eigenstates for A and B is the same basis. Okay, so every state in that basis is an eigenstate of A as well as eigenstate of B. Then it is very easy to see that they commute, because if I measure A first, suppose I have some eigenstate, some say X or whatever, or I call it something, okay, some A, which is an eigenstate, simultaneous eigenstate for both A and B. I measure A first, so I measure A with some, then I'll get A outside. When I measure B, it's an eigenstate of B as well, so I'll get again A outside. So first A, next B.
Doesn't make a difference.
So if I make B first, measurement of B first, again I'll get A, then A later I'll get again A. That means the order AB is equal to BA, or AB minus BA is equal to 0. That means A and B commute. Now what is most important is that the reverse implication is also true. That is, suppose you get two observables which commute, then you can show that they have common eigenbasis. That proof is long, so I'm not going to go into it. So it's both the things. That means it's a very powerful step. Commutator bracket or commutator, Dr. Gandhal also had mentioned that. So that is a signature of two operators which can be measured simultaneously, one after the other. That is,
Sure.
Same eigenstate.
Find that proof in any standard
You
good
can
book on.
find it,
The symbol for this, of course, is.
AB is equal.
But they both are operators, mind you.
Yeah.
So you should operate in that sequence. So that's something which is very interesting in the sense that measurement process is a bit tricky. I will also give a so uncertainty relation is related mathematically to the value of the commutator bracket. If the commutator bracket is non-zero, this is mathematical. Physically, as I said, if it has a definite momentum, I don't know where the particle is, and because it's a simple wave, and if I compress, exactly what you do in Fourier space, if I compress, of course I'm beginning to know where the particle is, but then I lose the spectrum on the momentum front, if t as you talk about it, right? So it's very similar.
There's a physicist description of a newly married person. He's in a state in which his momentum has definite value, but it is his coordinates are infinitely uncertain.
Yes.
It holds true for any non-commutative operator.
Any two measurable quantities whose operators do not commute, you won't be able to measure it simultaneously. Yes. So where I don't know what's implications in the quantum computing stuff, but if you, for us, the measurement of energy is h, which usually we try to measure the energy. Now what can you measure with this together so that you have a precise energy, precise P, yes, H and P will commute. So you actually start collecting operators which will commute. Now how about angular momentum? So usually the operator is L square that commutes. I mean, commutes in certain situations, all right. Then Z component of that. One of them you pick up, but I can't add LX, LY, Z in the same set. So that set is, I can't continue. I have to have it here. I take one of them, yeah. And you can add operators which, so this set is a commuting set, and as you mentioned, that means there is a common eigenfunction for. To find that is a separate issue, how to find it, but common eigenfunction for that. So that's interesting because it will have implications somewhere in computing.
One comment, can I do it? One comment.
Now let us then discuss and make the comment and anyway, sure.
On the board.
Oh, okay, yeah, sure.
So, I mean, I can make it from here also.
We don't want too much of mathematics. I mean, I don't want to give proofs.
Give any mathematics here?
No, I don't want to give any proofs because the proofs are there.
The proofs also I didn't give.
That, so without proof, yes.
What were we discussing?
We were discussing the set of commuting operators. Set of commuting operators.
So, how it is connected with degeneracy? That's what I. So, suppose, I mean, degeneracy means what? I mean, more than one linearly independent eigenstates correspond to the same eigenvalue.
I mean, do you know what degeneracy means in general? No, then they can sort of, then you have to explain.
You have an observable.
See, so that's what I said. If degeneracy is clear, then one can discuss the effect. Otherwise, one has to make degeneracy clear.
Yes. So, I am making that. So, if you have A as an observable, it may happen that there are, out of its basis, eigenbasis, there could be two states or more than two states which belong to the same eigenvalue of A. Okay? This is degeneracy. Okay? Now, what happens if suppose, I mean, there is A and B belong to the same eigenvalue lambda. Now, the reason why this happens is that there is another computing observable with A and which has common eigenbasis. But then that means this is an eigenstate of A and B both. But that has to be labeled by the corresponding eigenvalues of A and B. So that is A and A prime is here, suppose. Then AB and AB prime. So now they become different. Do you understand? So that is, I mean, when you have a complete set of commuting observables, as he was pointing out, and then you write the eigenbasis of all the common eigenbasis of all, labeling with the different eigenvalues of all of them, then there is no degeneracy. Then you will always get different.
See, what is an example? I mean, those who have done hydrogen atom, it's a simple example is an hydrogen atom. The states are degenerate in the sense that correct. And another remark, just a remark that degeneracies of a physical system are directly related to the symmetry. If you find a symmetry operation, then you will find, symmetry means rotational symmetry. Simple symmetry is rotational symmetry. If things are rotationally symmetric, which is Z by R, 1 by R potential is, then some eigenvalues, corresponding ones, will be degenerate necessarily. Now, degeneracies, I don't know whether they will occur in the quantum computing part, and if they occur, then must be taking care of it. So, that's something which is little more intricate, though it is commonly discussed because almost all states, one dimension, we discussed, has some peculiarities. So, whatever we discuss, I should supplement, which is not true in 2 and 3 dimensions. Any one-dimensional potential, so one should not have this idea that there is a bound state. One-dimensional potential, if it is attractive anywhere in space, has at least one bound state. That's a theorem that can be rigorously proved. That is not true in 2 and 3 dimensions. So, if I have a 3-dimensional potential, whatever, whichever way it is. So, this well rotate 3 dimensions. No, I am not sure In fact, there is a minimum width and depth of product is required so that you get at least one bound state. So every attractive potential need not have a bound state in 2 and 3 dimensions. 1 dimension, it's rigorous. Though although we discuss 1 dimension, there is a distinction, so one must make a distinction of that case. All right, so now I want to come to you, and whatever we have discussed in quantum mechanics as well as whatever the linear spaces that he has discussed, one by one, if all free questions if you ask, we are here. It's up to you, because there was a, I'm sure there is a disconnect, and he will, okay, before that, this is in fact a problem that in order to reduce the disconnect, you will never find anywhere in your quantum computing. You must have done, those who have done Qiskit business, you never encountered this, and still did lot of work, produced programs, ran there, got something. So where is this business of wave function coming in? Why do we want to study it? That's one of the questions that comes. But they take this one-dimensional example. So this is psi 1 of x. This is psi 2 of x. We use 0 and 1, so I'll use 0 and 1. That's the wave function that you have. And I have only 2, let's say, and the other one will be like that. That's the wave function, right? Now I say that I have a state. So I'll call this state as what? State 0, state 1. Underlying assumption is this state already exists. So in computationally I have solved this problem. In machines probably they already prepared the trap. Iron trap. There's 2 states. Yeah, but 2 of them they take. Lowest 2 is RU, so I take 2. Okay. And then the way you write your, wherever you did it, was actually alpha times or alpha 1 times 0 plus alpha 2 times 1. What do you want to write? I will call it U. That's what you dealt with. Where does this come from? This is given. This is this with energy epsilon 1, and that is that with energy epsilon 2, which you never had to worry about. But that's that.
There is a very simple device by which you can, any two-state system, you can use Pauli operators and this.
That's why 2-state systems.
Only 2 states.
So those 2 states are the eigenstates of some system like this. And you want to know what is the wave function if required, of course, you can solve the problem if you know the potential. And obviously these people, when you know, they have some potential in which they have actually created a physical quantum system. We created it here on the blackboard and solved it. They actually have a Schrödinger's equation truly, there is no question about it.
There is no isolated ideal two-state quantum.
So that's what you deal with and call this a, this is what you call a qubit. 2. Alpha 1, alpha 2, mod of this plus this square is equal to 1. And then deal with it.
Quantum particle with an observable which has only 2 eigenvectors.
That's it. This is the same thing. So it could be in 1, then it's an eigenstate. It could be in 0, it's another eigenstate. But usually it will be an
Alpha 1 plus alpha 2. So as I just said that there is no ideally two-state system. It is ideal.
That's true. But what you deal with is a 2-state. For you, it's a 2-state system. The 3rd state is taken care of. It doesn't interfere with you right now. If it does, we'll see. In fact, there are some 3-state systems.
एक अजून वरती आहेत. आता आयर्नचं घेतलं मी.
असणारच.
It is an ion. Actually, it has many energy states. In fact, infinite energy states. But the lowest two states are at rest. So you don't bother about the higher states.
The
Probability is zero.
the resonances and all adjusted so that you don't go, the energy required, don't go beyond first two. So for us it's a two-state system, don't have to worry about the rest.
यू जो आहे तो या दोन स्टेटच्या मध्ये आहे.
हा यू हे ते तुम्ही अल्फा 1 अल्फा 2 वर या यू याला सगळ्याला मिळून यू म्हटलं मी, तो सगळे ते त्यांनी यू बी लिहिलेले होते ना, ते याला यू म्हणा, याला U1 म्हणा, याला U2 म्हणा, याला यू म्हणा. सो इट्स अ क्वांटम स्टेट. मी हवा असेल तर मी असं लिहितो साय एक्स इज इक्वल टू अल्फा 1 टाइम्स साय 0 ऑफ एक्स plus alpha 2 times psi 1 of x, where psi 0 is that and psi 1 is that. No. I am trying to connect. I know that they are not involved. It's not a question of I don't know what it is. I am just trying to say that when they write 0 and 1, they should know what is involved.
Comments are for the audience.
Yeah. So what I am saying is, I am trying to tell them when they write 0 and 1, it actually means that there is an involved wave function somewhere. You don't have to worry about it. There is some function of this kind. You don't need to worry about it. It's there, buried, and it doesn't affect anything that you do. So the connection is this.
Are these people aware of Pauli operators?
You are going to introduce. Yeah, Pauli, yeah, you are going to introduce him because they need to know. Oh, of course, those who do Qiskit business must know that they are there, but they are matrices.
Yeah, we only think.
But they are unitary matrices, and he will explain how they are connected with the gates and so on and so forth. Any two-state system. So the connection comes exactly. Instead of doing all that, you just do this.
Corresponding to energy zero.
Sorry.
Eigenstate corresponding to energy zero. Eigenstate corresponding.
Now you can take this energy.
Energy one.
This energy to be 0 if you like, and that to be whatever the energy difference is. You just change the reference. So whether it is taken to be 0 and something I don't know actually in computing. So
I want to modify. I mean, I agree with what you are saying. See, when you want to do quantum computing model, then these wave functions are not required. But if you are constructing a computer,
then it is necessary. When it is necessary, what is there? There are several things involved. Otherwise, you will go. Yeah. So these are the problems that they need to address to actually construct a quant. Otherwise, it would have been easy now. Why it takes so much of? Spin is another one. Spin up and spin down, two states again. Call one as 0, but you can actually write down spin wave function, its corresponding space wave function, and so on and so forth. Fortunately, we don't have to write that. Even when do quantum physics, we just write it as up and down. This will also do, sure, because spin has only two states. Well, with qualification, it has only two states, but it could be a linear combination of these two. These are definite SZ basis, since he talked about basis.
spin up is given 0 and spin down is 1.
That's-
The reason is that energy wise spin up is lower energy. So minus S dot H now. That term is subtracted out.
It's with respect to a magnetic field. Otherwise, both are degenerate. If there is no magnetic field, then doesn't matter. If you put a magnetic field, yes. So the lower energy state is taken as because that's a magnetic moment. Spin is another concept. Where do you think spin comes from? Where do you think magnetic moment comes from? Just as engineers, you have a lot of magnetic moment stuff, right? So, but I have a current carrying coil also gives me a magnetic field. So,
Electrons move.
so the electrons move, they generate a current, and I can do some fancy arithmetic and algebra and tell you that it generates a magnetic field, whatever that effect is. So, is there a difference between this and the magnetic moment that we have. Is there a difference between iron generating a magnetic moment and a current carrying coil generating a magnetic moment? Operationally there is, that you know. So where does the magnetic moment of iron comes from? It comes from inherent, right, spin of the electron. Now student asks question, my answer is simple. Student, how is it electron rotates or something like that and generates a, no. It's a inherent property of an electron, just as you and me have certain properties. We have our own this, that, what not. So it's an inherent property. Let's not ask question where does it come from below this question. So it has this, that's all. It has spin. Every electron, well, why every neutron has spin? So neutron has no charge. It has spin. Right. So I can't say that spin is because of any charge or something. Neutron has spin.
Fundamental particle is characterized by
So
By
spin.
electron spin, we don't have any.
Neutrons, many particles have spin. So spin is a property of certain class of particles. Certain class of particles do not have spin. That is the spin which creates magnetic moment, and that gives us the iron or whatever people are talking about, strong, the ones which China holds, the rare earth magnets. After iron, it's that, and we don't have it. That's purely the natural this thing. People try to create now, they are creating magnets and so on and so forth. So that's part of it. I would probably make a interpretative comment on measurement. Measurement has been talked about, and I want you to ask the question of measurement. My interpretative comment on measurement is the original, the way it is stated in quantum mechanics books on what the measurement, the expectation value. Exactly whatever has been said about expectation value is correct, right? So let's do the following. Experiment. What do you get an expectation value? So there is state psi. It could be eigenstate, it need not be eigenstate. It's some state of the particle, single particle. Actually it's true of single, many, whatever. No, I know, I'm just trying to be generalized that I don't have to worry whether it's an eigenstate or not. I know if it's an eigenstate, it will get the same answer. But no, but that's what I'm trying to make it clear, Pramod, that they need not have an idea that it has to be non-eigenstate. Even if it is an eigenstate, the interpretation works. Same interpretation. So you prepare a state, I don't know whether it's an eigenstate or not. You don't prepare one state, you prepare identical. This is a conceptual now. You prepare identical systems, how many millions? Let's say thousands. Because you can't take million. It's a funny way of, they are identical. They're doing nothing with each other. Then you have a measurement apparatus which is here. So many. You want to measure energy or whatever, energy you want to measure. Then you have thousands of students who are available for doing a measurement. You raise your hand and say, when my hand is raised, make a measurement. Identical copies. They make a measurement. Then they measure something, let's say is the energy epsilon 1. He measures epsilon 1, he gets something. Now take an average, right? Now take an average. That's what is the interpretation of expectation value. That's how the measurement was interpreted in the Copenhagen interpretation. Part of it is. The second part they have discussed many times, that if you make one measurement, that's why there is not one measurement. a corollary of this is, of course, as they have discussed, you can take a copy, measure, another one, measure, another one, measure, another one, measure, but a different, not that same one. Thousands of you create, send it for measurement, create, send it for measurement, take care of, which is same as that, this. But as they have discussed many times, that if this, so I write that, okay. Now I would ask a question. So, as he has discussed, Anjali has discussed, what should be the phi n's? I am expanding my state in terms of phi's. And I am measuring some energy. My operator is H. So what should be this? Let's see whether discussion they have understood. So psi is a general state which is prepared for a system and an electron somewhere. I want to make a measurement of energy. So that's the operator is H, and I expanded mathematically in terms of phi, phi 2, phi 3. So is there any relation between this and that? Or they are arbitrary? Correct? No, correct question? Should they be eigenfunctions of H?
The system is in state psi.
It can
That is on the left
basis
hand.
of-
I measure H on psi.
So I have to make an expansion in terms of eigenfunctions of the operator I am measuring. So phi necessarily means that H on phi n, this is what I want to, this is the energy of the nth state. These are eigenfunctions. That's why, right? That's why I expanded the state in, if I want to measure something else, I take that set and expand. The rest is clear to you. Now if I make a measurement, and suppose I get epsilon 3 as an answer, the next question, that means one measurement I made, just one, and I get an answer epsilon 3. Immediately I make another measurement. What should be the answer?
Same.
Epsilon 3 was epsilon 3.
You again measure, it can be anything. Even to
I said, okay, immediate measurement to make it
after
clear.
E3, after E3 you will measure.
Yeah, I measure once I got E3, immediately I measure E3, then E3 only, not anything else. Only E3, right?
Collapses to these.
Correct. So that's the point. That I will always get E3. Of course, if I make sure that it evolves in time again and then it restores its original state.
When you get E3, that means you are getting the corresponding eigenstate corresponding to E3.
Correct.
Any eigenstate, if I make a measurement of that observable, eigenstate will continue. There is no change in eigenstate.
Is this part clear? Why I would get E3? Everyone.
If it collapses, then it will get E3.
Is it clear or I'll make it clear? I mean, people know.
That's an eigen.
Others.
You can make such figures. It collapses to 5. So again, if you measure,
Yeah, it collapses. Yeah, I'll correct.
You get the corresponding result and eigenstate will not change. It will come out unaltered. That is how eigenstate is defined, no? That's how we define that.
or you mathematically you can't.
I'll assume that it is somewhat clear, or it is somewhat. So which part is not clear?
That is
Why-
also not clear.
Why it is not absolutely clear? Why it is not absolute? Because this is the crux. This is the crux of measurement. When you are going to do quantum computing, you are going to make a measurement, and then what you get, if you don't know what you are going to get, you are not going to get your answers. So is it absolutely clear? Because this is the point, I think this is the only point you should sort of pick up correctly, empirically at least.
If you have a superposition, some state, you are measuring H or whatever, so you expand it or you write it as a superposition of the eigenstate of H in order to understand that measurement. I make a measurement on that state, I get some eigenstate out. So that means the superposition is lost. After the measurement, I don't have superposition available. Only one eigenstate comes out. And then if I measure again on the same eigenstate, then that will continue. Measurement of an observable on one of its eigenstates doesn't change the state. It just what happened to the electron? Electron got died.
No, electron got into this state. So let me draw the diagram that you drew. So something like that you drew, isn't it? So this is 1, this is 0, and then this is your quantum computing states that he will discuss later on, where say 0 plus 1 with outside whatever factor is alpha 1 and alpha 2. So that alpha 1 square is, no, alpha 1 square is say 0.9 and alpha 2 square is 0.1. Mod square. Take it real and that will be square. All right. Sure. Now I don't know. So you made a measurement and I got 0. Now you started operating on this. You don't know what has happened. It's either here and here. And now you start operating on this because you want to make something further. Then you are going to operate on 0 only. This is gone. This original state is gone. If you don't realize that this has happened, then your operations are, if you realize what has happened, then you have correctly done whatever is to be done afterwards. That is your algorithm, what you want to do. Correct. So if you make a measurement, if you don't make a measurement, well, then it doesn't matter. But if you make a measurement, this is the...
Electron is no more in spinning mode. Before that was in spinning.
Oh no, we have gone from that discussion of the real space to what he said as you have only two states. So electron is either in this state or that state, linear combination state. So the electron has been collapsed, dropped down, forced into, in this case if 0 is the answer, into 0, 1. So now if this is the case, electron is here. After the measurement, initially electron was here plus here. After the measurement, it is here. If the answer is this, after the measurement, it is here.
Again in superposition by doing.
Oh sure, I mean later on some jugglery, some operator will make it in a superposition again. Sure. That depends on the circuit. Sure.
Some other state.
Yeah. You can do that. Sure. It's available to you.
But if you make a measurement of the same eigenstate of that same operator, then nothing will change. It will come out. Measurement on an eigenstate of an operator will not change the state.
So
After applying certain operator, it will change.
after this, if you
On an eigenstate, if you make a measurement of an eigenstate of that operator, then no change will occur.
This is the definition.
So if you do, if this is 0, and then that is 1. Make an energy measurement, you will definitely get 0. You will never get 1, you will get 0. That's how the whole thing works. So this much of measurement.
In expectation, we need multiple measurement. So we are not having a copy of same electron. Electron cannot be copied.
Okay, yeah, then that he will explain why it cannot be copied. But let's do the following experiment. No, I mean this, that non-copying, that the no cloning theory, you will explain that. So let's have alpha 1.
For expectation value, we need multiple measurements. We need to have multiple copies for measuring.
Wait a bit.
You can make them by actually preparing.
Wait a bit.
Copy it like a Xerox.
Alright, you prepare, there is something like you prepare a system. Initial, time t is equal to 0, those who you use Qiskit or whatever. Now, if this is the way you have prepared it, let's say somewhere this is the case. Now you make a measurement once. You will get a 1 here, nothing here, 0, there is nothing here. You make a measurement twice. Now you leave this, prepare the system again in the same state. Prepare the system again in the same state, make a measurement. So what will the answers would be? He wrote that down. I could get 1. Suppose this is 1 over root 2. This is 1 over root 2. No, 1 half. Half. 1 over root 2. 1 over root 2, 1 over root 2. Right. Square is, yes, 1. What do I expect to get an average? Let's make many measurements. Every measurement, I prepare a state of this kind. How to prepare a state of this kind, he will tell you later on. But you prepare a state of this kind, make a measurement. I got 1. Prepare a state, I got a 0. I got 1. I got 1. I got 1. I got 0. I got 0. I got 0. 10,000 times. If you take the average of how many zeros and then divide it properly, you will get approximately half for this and approximately half. Approximately, I am not saying you will get an exact half. So approximately half the time average with an error. Now you don't like an error, you make double the measurements. The error will reduce. It's a law of averages. Standard. That's why, and that's an expectation value. Half.
Exactly same electron we can prepare.
Same state, yeah. If you want an electron, you say electron, but it's a state, exactly state you prepare million times. Yeah, take the averages, yeah. Sure, whatever you are measuring. Yeah, so no, in this case you will get epsilon 1 plus epsilon 2 upon 2 if you make the Hamiltonian, energy measurement. Because half the time it is in this state, half the time it is in that state. But if you actually measure the state, as he says it can be measured, then the state will give you half the time, half this one. And in this state I know the energies, so epsilon 1 plus epsilon 2 by 2. Average of 2 energies. If you make, now it depends on what you measure. You measure energy, yes. That's how the measurement average expectation value works. Expectation value of the operator. State varies like so. So we have taken the average. Exactly the way it is written originally. Anyone else? Any question? Anything?
Communication when sender is sending something, receiver receiving, then receiver not having multiple copies.
Hold on. Let's go to communication next week and then let him talk about the other things and then you ask that question.
Sender responsibility is there to send multiple.
If it flips for the, less than half of the number of times, then the receiver says that 0 is complete.
But that's outside this.
That is one kind of overhead. Binary, classical, only 1 bit is sufficient to send.
Ideal, but then there is a probability that
You also have a patching and so on and so forth, and error code, error bits, send it back.
Ideal.
So you lose bits.
On the way it becomes 1 by noise. You will get 1.
Yes.
You will never know. You will assume that 1 is communicated.
Yes.
Totally wrong. But if I send you 3 views, the probability that
Let me interrupt. This is outside the scope of, so let's not discuss that. I'm sorry, this is not the question that I want to discuss today. So this is a question that he will discuss at appropriate time, because this is something sending qubit, receiving. We have not come to that stage. Something related to quantum mechanics and its relation, yes. Something related for tomorrow's or day after to next week's talk, that week. चहा आलाय का? चहा आला असेल तर चहा घ्यायला जाऊ. झाली का वेळ? न चहा झाला म्हणजे वेळ झाली. मग चला मला 3:30लाच थांबवायचं.
Just a small announcement. Kunsal has a small matter to attend, but
Okay.
after tea there is a lecture from Jay Mangaonkar of QPreo. So it's part of the industry session. So please take part in that also. QPreo, it's a quantum stack. Startup. Here, na? Yeah, 4 to 4:45. Yeah. And tomorrow also same. There's no